All right, great. So we're right on time. It's 10 a.m. and we have a couple of people here. So thanks a lot for being here. Um, so to kick off the meeting, it's my pleasure to have the uh, director of AIP, Masashi Sugiyama. He's going to introduce the center. And let me also say that part of the funding for this workshop actually came from AIP subsidy budget. So it's thanks to him and his team that we have this event here. So Masashi, take it away.
Okay, good morning, everybody. I'm sorry that I can't attend the workshop physically because I'm traveling in Osaka now, but it's my great pleasure to introduce our RIKEN Center for Advanced Intelligence project. So I'm director of the center. So welcome to the second Bayes-Duality Workshop. So let me start from this slide. So what is RIKEN? So RIKEN in Japanese is actually consisting of 6 letters. And the first 3 letters are pronounced as Rikagaku, and the last 3 letters are pronounced as Tenkyusho. And they mean, so the first 3 characters mean so physics and chemistry. The last 3 characters mean research institute. So a long time ago, RIKEN in English was called Research Institute for Physics and Chemistry or something like that. But actually 6 letters is too long for Japanese. And we usually take the first character and fourth character and attach them. So this is in Japanese pronounced as RIKEN. So ordinary people in Japan call us RIKEN. So then at some point, the RIKEN headquarters decided to use this Japanese acronym as the official English name. So this means RIKEN in English is no longer an acronym, but this is our official name. And RIKEN actually has a relatively long history, started in 1917 as a private foundation. And then later on, so RIKEN was actually quite successful and it got bigger and bigger. So in 1939, so RIKEN had 63 companies and 121 plants. So it was called RIKEN Concern. So RIKEN was so good before the World War II, but because it was so good, so it was regarded as a kind of dangerous entity after the World War II, and it was broken up after World War II. But in 1948, RIKEN restarted as Scientific Research Institute, and then later on, it became public corporation. And now we are so-called National Research and Development Institute, and we have a new president from last year, Gonokami. And entire RIKEN has about 3,000 researchers actually. It's a big entity, and we have about 500 admin staff. And roughly, so we have 15 research projects and centers. And they are very roughly, so 6 are physics-related research centers, and six are life science-related centers, and 3 are informatics research centers. So they are robotics-related center and high-performance computing research center. Then our center, the Center for Advanced Intelligence Project. So then what is RIKEN AIP? So RIKEN founded the Center for Advanced Intelligence Project in 2016 under the Ministry of Education, Culture, Sports, Science, and Technology. And we have about 130 employed researchers, and 40% are international researchers, and 1/4 are female researchers. So these are reasonably diverse as a Japanese institute. Then we have about 250 visiting researchers from mainly domestic universities and industry. Then we have 130 domestic students as part-time researchers. Then we have more than 140 international interns in total. And we have many international collaboration partners and industry partners. So we are located in the center of Tokyo. So this is where you are now. So we are on the 15th floor of this building. But in addition to this Nihonbashi office, so we have several distributed offices across Japan because some teams are located in different universities. And RIKEN AIP has 3 research groups. And the first group is called Generic Technology Research Group. So here we have 13 teams, and MT is here, and Kenichi is here. So they are a member of this Generic Technology Research Group. So in these groups, researchers are studying like learning and inference algorithms and also like statistical and optimization theory. Then in the second group, called goal-oriented technology research group, so we have 17 teams, and there are roughly two pillars here. The first pillar is AI for science. So we are interested in some like science topics that are quite active in Japan, like cancer research, material science, and genomics research. And the second pillar is about AI for societal problems in Japan. So we have a lot of natural disasters in Japan. The elderly health care is an important issue in Japan. And also education, this might be universally important over the world. We are working on these societal problems in this goal-oriented technology research group. Then finally, so AI in society research group. So we have 6 teams here, and they are working on more on the societal side of AI research, like personal data management, AI security, economy and management, ethics and governance. And we have more detailed research slides here, but maybe I don't really have time to go into the detail, but we are enjoying doing research, and I think we are making a lot of important progresses in these fields. Okay, I looked at the program, and this is wonderful. A lot of great speakers are here, and I wanted to really attend the workshop. It's a big pity for me. But please enjoy the workshop and hope that this is a fruitful experience for all of the participants and speakers. Okay, thank you very much.
So this is the second edition of the Bayes-Duality Workshop, and we did something much smaller last year, and it was not streamed also live. So we try to go a little bit bigger, try to reach more people this time. But before telling you anything, I just want to start the meeting by thanking people instead of ending the meeting by thanking people. So this was really a lot of work because we try to go a little bit bigger scale this time. That I really want to thank the people who've been working tirelessly for the last 6 months. So Tomoko, are you here? Yeah. So Tomoko, Harumi, they're standing right there at the back. Ikuko, is she here? Ikuko, can you stand up? Yes. And Ugo, are you around? Okay, yes. So yeah, I think they have been working for the last 6 months. It's a lot of work. So can we give them a big hand? So thanks a lot. It would not be possible without your help, and I know how much you have sacrificed for all this. And we have other people sitting here at the Zoom table, perhaps. So Songbai, Clement, and I have not met Satoki yet, and Kenichi, Kanji, and Koichi for helping with posters, and Keigo, Dharmesh, and Zidong, they're organizing the socials. So the first social is on Friday, and it's if you want to actually attend that, Dharmesh, Zidong, can you stand up? Keigo, I don't know if Keigo is around. Yes. So please talk to them if you want to have drinks on Friday evening. They have actually posted this on Slack that some of you are on. Okay. But also big thanks to all the assistants from OCD, and I think I cannot, they're not all here, but they have, people at the registration desk and lots of people who have communicated with you through emails. We are government funded organizations, so there's a lot of paperwork, but they really do this and also be polite at the same time. So this is an impossible task. So thanks to them, and also thanks to Akira Takahashi, who is who heads the Office of Center Director, and of course Masashi, who we just heard from. And thanks to all the people in the group. And Kenichi, are you here? Kenichi, yes, Kenichi, who will be around, and you've heard from him. And Rio, I don't know if he's here yet. And Julian, who will arrive next week. So these are co-PIs in the thing. So let's do a big round of applause and please hear about it. All right. Okay, so I just wanted to give a little bit of overview, not go too much technical, but just try to make you see that this is not a thing that just appeared like when we got the funding, or we didn't made this thing up. We've been thinking about these things for a while. Okay, so I just wanted to tell you, like, for many years, I was actually really interested in quick adaptation. So this has been something that I've been thinking for a very long time, almost 20 years. How can we design intelligent machines that can learn as quickly as humans and animals? So doing something like what our kids do, and you have seen these videos of my kids, and I love my kids. So I show them again and again, and I'm sorry if this is bothering, but they're so cute. So they learn like this, and this was like almost 10 years ago when I made this video, and I've been showing it for 10 years. Now my daughter, is quite old now. She's not this big, but I have another one who's this big, and I'm still mesmerized with this. So kids can really learn, by random exploration of the world, and their brain really learns something in the end, something meaningful, right? Like this, and they have so much fun, right? And they can actually adapt their skill from one situation to another situation in a very novel way. Something that we don't understand how it works right now in machine learning, right? Because as an analogy, our machine learning systems are more like this, you change a little bit of the surrounding, and they have no idea. They just like walk through it and catastrophically fail, right? So despite many people saying that we have all problems solved and we should all work on LLMs, our big pre-trained model, I don't think we're there yet, right? So like 20 years ago when I was thinking about these things, have many things changed? I feel like no, we're pretty much at the same place as what I think. I mean, of course we have a system that works extremely well, but it learns in a very artificial way. So it is artificial intelligence, I guess, but it's, there's a lot of issues with the system. So of course, big amount of resources are required, and only some people can afford it. And I know some of you are from companies here, and I want to talk to you more about this. So, I think we need to democratize this. We need more people access to this, because this is going to be a problem otherwise in the future. I think a few years ago I had to say more about this, but now we all understand. So I don't have to tell you, I don't have to motivate you, because we are already there now. We need all of these things, and we are taking it from people, and we are not attributing people who have actually powered our great system. They are not getting anything out of it. They're all getting, all the cost is actually borne by them, right? Environmental cost, but also all the harmful, dangerous behavior that's going on, right? This is quite bad. Anyway, I've listed a few things, but the systems are not really like they're not cute like our kids, even though we think that they're conscious or something. But they cannot do simple things that kids can do, like without any effort, right? So there's something broken here. There's no like order in learning, like learning things that are simpler first, learning things that are more complicated later. There's no such thing, right? So I think this is kind of what leads to this very dangerous, untrustworthy, harmful thing. So one thing that I really want for us to think in this meeting, how can we actually solve this problem? So this is kind of what our goal is. Our goal is that we want to fix this, and this is what we want to do. And I really believe that Bayes duality is a potential solution. I think it really hits the foundation of all of this. So that's what we are doing here. So one problem that we have kind of set, and on June 18th on Tuesday, it's a CREST day, so don't miss that one. We're going to talk about this big problem of what we really want to do. So we want to know when and how and why can we adapt quickly to changes. Sometimes we can, sometimes we cannot. So how strong is our AGI? Can it really be better than humans? Can it go over the conflicts that we have in learning? We learn one thing, we can't learn the other things. But these questions are not really answered right now. We don't know what these machines are capable of and what kind of bad things they're doing, because they're actually not capable of doing that, but we still believe that they can do it. So we need to kind of really tackle this fundamental question. Okay, so that was the big so this is the kind of problem that's the main goal. And just to show you the pictures of people, so we got this grant in 2021, right, with these co-PIs. So it's a joint grant between France and Japan. And the Japan side is headed by me, and the France side is headed by Julien. And we have two co-PIs who are in Japan about this. And the main kind of idea, and you will see this slide a couple of times, is basically that you should start to think about a system that is made up of components. And if you want to understand that you want to change the system, then you need to go in there and figure out what parts are easy to change and what parts are difficult to change. And the parts that are difficult to change, then you need to think more seriously about them. So it's kind of trying to formalize this and going to the basics of it, that this is rooted in perturbation, sensitivity, and duality. So that's how the word duality comes up. And essentially, we are trying to do something. I mean, you could actually say it's kind of generalizing Taylor's method. So just local linearization and perturbing, and you can trivialize it like that. But I think there's much more to it than that, because we are now talking about model that's kind of made of certain things. And the simplest thing that you can think about is data, right? So simplest idea, if you think about what is duality, and I'm confused about this, then think about perturbations to data. That's the simplest perturbation that you can think of. And essentially what you want to understand, that when you change the data, the model changes, and you want to understand how it changes, and when is it changing in your favor, when it is not, what kind of data I should be adding, how I should be adding it, and how much of past model I want to keep, how much I want to change it, right? It's very, very simple actually in this sense, and you can write some fundamental equation for this, like one of them is written here. So talk about this on 18th, on Tuesday, on Crest Day, we'll give you some things that we have come to. But these equations are actually, they are kind of discussed in the community, but they are kind of byproduct of a Bayesian equation that's foundational, is how we come to Bayes duality, right? So we believe that this is true, and we are finding more and more positive signal for the last few years working on this, that there is a very fundamental equation, and I've written here, and it's funny thing is that if I show it to Bayesians, they don't understand. But they will say, I've never seen it like that, but this is actually Bayes' rule. And so it's so weird, because it's written in such a new way, it's hard for everybody to understand, so we get bashing from everybody. Like optimization people will say, oh, I knew this from a different angle, and then Bayesian people will say, why don't you just write probabilities? And I want to stick in that, and so different people see it differently, but I think this kind of unifies everything, and it has like all the components that you have model parameter and you have training data. It's kind of a representative theorem that you can perturb the training data and the solution will somehow change. And this helps us to see everything. Anyway, I actually gave Nirup's tutorial about all of these things, and I wrote a long paper, and I thought my work was done. But I've accepted the fact that my work is always starting, and I'll spend my life just explaining this equation to people. So yeah, it's actually quite simple in that sense. And you may think that maybe this equation just came out of nowhere and I'm just pushing my own research agenda to other people. But actually, it has taken me almost 20 years to come to this. So I've worked on many, many things. And perhaps the first time I actually realized this was really 2009. So this was a long time ago. When I was doing my internship in France, I actually realized that when you write down the solution of Bayesian objective, variational objective, you always see this kind of things where there's some contribution from the data, there's some contribution from the prior, and they're kind of put together in a very specific way. So there's some kind of parameterization that you can think about, and it always defines the problem. And I realized later on that Cedric Archambault, I don't know if some of you may know him, but Manfred Oper has already written about this in 2009. And so then in the following year, I actually tried to generalize it during my PhD. And I was able to do it for GPs at first, and then I was able to do it for a slightly more general case. This was 2013. So this is like the only paper that says dual in it. It's really using convex duality at the time. But then got stuck here because it requires convex things. It got stuck. And so I kind of gave up on this. I talked to David Bly in 2014 and he said, oh, this will never work because it needs convexity. He was right? But then I started doing other things and I came up with this paper that when I actually wrote this paper in AI Stats, I just moved here and I told my wife, I did the biggest thing that I could think of. I should be famous now. And she's still asking me, like, are you famous now? What happened to that? So actually, this was a big deal, actually. So you would say that all the papers that we wrote in our group, they're all originating from this single paper. It's been cited like less number of times than other papers that I wrote on deep learning, right? So yeah, so that's how it works, right? But this is really, it has all the thoughts and it has a really bad title, as you can see. It has like conjugate twice and inference twice and variational twice, conjugate 3 times. It's that important. So yeah, I didn't know how to write it at the time, but now I know much better and I'm trying to communicate it in a way that makes sense to you. And in 2019, I kind of realized, maybe we wrote this paper where we realized the connection between neural network and GPs. And then that clicks how duality actually comes in because it's in the function space, in the data space, in a non-parametric way. It's something related to what people call dual in convex optimization, but it's also related to duality in information geometry, which is quite fantastic. So I started talking to Kenichi, I think it was in the Toyo Cafe outside, and he said to me, you shouldn't just think about doing something technical, maybe you should think about aiming for, something foundational, starting a new field, because that's the biggest contribution a scientist can make. So he encouraged me, and then Rio was always around talking about things, so we start thinking about this in 2019. Then we wrote in 2020 something, and it was accepted in 21. Now, why I give all these things? Because I want you to understand that this is not made up, right? This is being thought through quite well, and I want to convince you that all the pieces fits well together. And I am sure that the problems that you are thinking about, the things that you are solving, they are somewhere in there. And if they support what we say, about Bayes-Duality, that's great. But if it contradicts, we're even more interested, right? Because we want to see how wrong we are or how correct we are. So we're very happy to have all of you here. So last year we only had like 30 people, and this year we have a lot more. So I think online about 130 people have signed up. I don't know how many of them are watching right now, but total workshop, we have about like 24 talks, 6 tutorials, lots of posters. So around 10-15 students have also joined. Originally, we wanted to do a summer school, but our funding didn't work out because our funding is not for students. So I apologize that I was not able to invite people, but we still have people. Some people have come from India. I'm very happy that we were still able to, have maybe 7-8 people who needed visa and were given funding by us or by their institution. They were able to come here. So we have some students, and hopefully next year we can fix this and we can do 1 whole week of tutorial for students and then 1 week of talks like what we're doing next week. Okay. So the goal is really, we want to make sure that our project's goal is okay. So any feedback on anything is welcome, and we really just want to talk with you, maybe convince you, or maybe get convinced about your problem, why that is important for us to look at. Essentially, we want long-term collaboration. We are really into slow science. We don't have to rush anything. Yeah, so we're really about science. And I actually met with the people who have actually running this funding thing for us just 2 days ago, and they said they're not looking for some LLM being trained or some big show. They really want us to advance science. This is incredible, So we got all this money, and we have this opportunity to do something here, good for science and society, with no flashy things. Right? So that's what we're doing here. So this is the program. It's quite standard. We have some coffee breaks. So today's coffee break, unfortunately, and I'm sorry, Vincent, he's going to give the talk, and because I had to do this bit, and Masashi also had to do for 10 minutes, we ended up taking the coffee time, but we're hoping that when we're doing question answer, there will be coffee, and you can get up and you can serve yourself, but I hope it doesn't affect your question answer, so I apologize for that. But we have lots of, so like blue is talks, and then we have tutorials. So thanks to all the people who have actually offered to do this tutorial. And we have lunch break. We go at 12:30. So 12:30 is a good time to go because everybody goes at 12. And then, yeah, it's really kind of fixed. So elevators are full. So I recommend you to like stop at 12:30, get together with some people and take 15 minutes to then go down. It's 12:45, then you reach the restaurant at 1. There are lots of wonderful places here. I think Ugo has posted something in the workshop channel for the list of restaurants. If you're looking for a vegetarian restaurant, there are a couple of people who want to go. There's lots of Indian restaurants where you can get vegetarian food. So you can get together with them. Hopefully you'll find each other. And if not, ask me and I'll connect you. So yeah, CREST Day on 18th, we'll showcase our research. So it'll be great if you can come to that. And we also have panels on 3 days. So panels are slightly longer. So hopefully we can do it informally. Panel, like I've assigned some panelists, but everybody can speak really. Like we hope to have a discussion. So it shouldn't be that formal because this is a very small meeting with like not too many people in there. Okay, so maybe this is an important thing. So if you're here in person and you have QR code that was sent to you, it'll be sent to you every day. Please keep it in your phone all the time. Otherwise, you won't be able to get out from 6th floor. So it's very important. And join Slack if you get stuck somewhere, then you can ping us and then we can come and get you. I'm sorry, I don't design this building, so I cannot do anything about that. But we are very privileged to be in this very expensive building where you can see Tokyo Tower outside if you haven't seen it yet from that building. And you could have seen the sky tree from this side, but somebody made a building just 2 months ago. So you can't see it now. So, okay. Yeah, so with that, I will end this and we can move on to our next, our first talk of this meeting. It's my pleasure to introduce Vincent, who's a tenure-track research group leader at Helmholtz AI in Munich, leading the group for efficient learning and probabilistic inference for science. He's also a junior faculty at TU Munich, a fellow of the Konrad Juice School, sorry if I pronounced it wrong, for reliable AI, affiliated with the Munich Center of Machine Learning as well, and a Bronco Weiss Fellow. His research focuses on reliable and data-efficient AI approaches, leveraging Bayesian deep learning, deep generative model, meta learning, pack-based. So he did his PhD at ETH Zurich. He was also a research fellow at the University of Cambridge, and he's a member and unit faculty of Ellis, and he's reviewing and doing lots of service work. He's also co-organizing our AABI, so thank you for that. We need that. It's Advances in Approximate Bayesian Inference, so I think it will be there at ICML. Yeah. And you're also involved in the I Can't Believe It's Not Better initiative. Also, that's a workshop or conference or something. Yeah. Okay, so yeah, it's great to have you here, and I think Vincent is a rising star in Bayes, so let's listen to him, what he has to say. Thank you.
Yeah, thanks for the kind introduction. If I had known that you would read out the whole thing, I would have made sure to write a shorter bio, but yeah, cool. I'm very happy to be here. It's my first time in Japan. I'm also quite impressed by how much on time this schedule is so far, but having seen the trains here, it's not surprising maybe. I'm also happy that I'm not stealing your coffee at least, and that you can get that. I was a bit perturbed about that, but I brought my own matcha here, so I should hopefully stay awake for the next hour despite the jet lag. Yeah, as Santi said, I want to talk about Bayesian deep learning today, Bayesian deep learning in the age of foundation models. And I also had a few of these existential questions in the last year or two, right? Or at least people have been asking me, is scale really all you need? Should we essentially stop building kind of clever little Bayesian models with cool priors and smart inference and just, like build a dumb model and throw it on a billion GPUs and then it's just going to run and, just drop everything and work on LLMs. And I want to echo what Emti said in the introduction, that I think that no, we shouldn't, right? Like that there's still a lot of open fundamental questions, and that maybe now more than ever, we should actually, go back to those questions and try to assess them through the lens of the progress that we've made in LLMs, right? So I don't want to downplay the progress that we've made with all these foundation models, but I think there's a lot of open areas where these models can still be improved. And I believe that we can all work towards that improvement through the Bayesian paradigm. So today I want to essentially talk about three little areas where I think foundation models can still be improved, or where I think we can make progress, especially with Bayesian methods. And these are interpretability, computational efficiency, and uncertain belief updating, or maybe I should say belief updating under uncertainty. And I have three little vignettes of kind of projects that I personally worked on that I want to showcase to show what I mean when I say these words. So we're going to start with interpretability. And this is a project that we're presenting at ICML this year. This was joint work with some nice colleagues at ETH, including Alex, who's also here. And the idea was that we're looking here at certain critical applications where you might need an interpretable model. So typically clinical applications or medical applications in general are one of those, where if you have a machine learning model that gives you a diagnosis or a treatment recommendation for a patient, usually the doctors that are treating this patient want to understand where that comes from, right? They really want to understand what the model is doing and where this prediction comes from. And so what they often do in those cases is to use model classes that are inherently more interpretable, including, in this case, additive models. And so what we did in this paper is essentially taking an existing model architecture, namely a neural additive model, and asking ourselves, can we make this better if we're being Bayesian, right? So this is, in some sense, a bit of a common theme of the stuff I'm going to talk about today. So what are neural additive models? So the idea of an additive model in this sense is that if you have data that has different features, instead of taking all the features and just showing them into the model, you actually have separate models per feature, right? So this is kind of these f of kind of x1, x2, xd, so where these like x subscript something are going to be features of the data. And so visually, essentially what happens is you have a feature input vector, and that kind of each feature goes into a different neural network, and in the end you add them up. That's where the additivity in this model comes from. So why would you do this? Well, if you do that on a data set where you can interpret what the features are, you now actually get curves, response curves that tell you like how the output that you're trying to predict depends on the features, right? So here's the classic California housing data set. And you can ask, how does the house price in California depend on the longitude? And you see there's kind of little bumps around, the Bay Area, for instance, and Los Angeles. And you see generally it goes down as you move closer to Mexico, kind of. So that might make sense to you if you understand what California looks like as a place. And also if the median income of the people living in the house goes up, then the house price usually goes up. So richer people buy more expensive houses. That also makes sense. So you can use these response curves to interpret the model. And I want to already preempt the question here because I often get it, like people often say, oh yeah, but I can take any model and get these kind of curves by using methods like LIME or these kind of like linearization methods. But what I want to really stress here is that this is really what the model is, right? So like once you look at this curve and you say this curve makes sense, then for all predictions the model gives you, like this is going to be the curves it uses. Well, obviously, if you use a kind of local method like LIME, it will like locally add some data point linearize and give you some interpretation, but you have no guarantee whatsoever that on any other data point that you might not have seen yet, it will still use the same response. So this is a very kind of strong guarantee on the interpretability of the model in some sense. Okay, so now obviously this is a stark assumption that really kind of, in many cases might not hold in the real world, right? So often the data is probably not actually structured in a way that the true function we're trying to model is additive. So we're clearly losing some amount of fidelity of the model in exchange for this interpretability. And our question was, within this very restricted model class, can we get back some of that performance by being a bit Bayesian about things? And so we use in this particular project linearized for class inference, which is also something you might see a bit more in the rest of the talk. So this is something that particularly Alex has worked on quite a bit and might talk about later today. So the idea is very simple, namely we take our trained model at some mapped parameter, which we here call theta star, and then we compute the Jacobian, right? So we do a kind of first order Taylor expansion to linearize the model. And this is actually our new predictive model that we use, right? So we don't actually use the full neural network anymore, but we use this linearized version. And then to get a posterior, we can just use kind of the Laplace approximation around this, and then you get this GGM posterior. So what that means in the case of additive models is quite nice. So because the model is additive in F, that means it's also additive in the Jacobian because that's a linear operator. So it's linear in all these parts that we care about. And that means that by implication, it's also additive in the uncertainties, right? So if I get a new data point and the model tells me it's uncertain about that, I can actually ask which of the features is essentially responsible for that uncertainty, right? So if you go back, for instance, to this California housing idea, if I get a new house that has 1 million rooms, then the model might be very uncertain, but it can tell me, oh, I'm very uncertain because this thing has 1 million rooms and I've never seen a house with so many rooms, so this is weird, right? As opposed to just telling me, oh, I'm uncertain about this data point in general. So this is yet another level of interpretability that can be quite useful for practitioners to have. Another nice thing is that the marginal likelihoods kind of separate over inputs. So this is just an approximation, and it's actually like, if you want to be more technical, it's kind of like a lower bound, and it depends a bit on essentially the off-diagonal elements. So the correlations between the different feature networks. But typically we would assume in this case that there's very little covariance between different feature networks, so that usually this approximation holds quite well in practice. And what that means is that we can use marginal likelihood model selection, which is another thing that we really like to do, for selecting different features. And we will see that's kind of one of the big advantages of our method that we're going to showcase, is that if we have features that are less important or essentially not important at all for the prediction, we can really effectively regularize them out of the model.
So what's the approximation in the second line?
The approximation in the second line. So yeah, maybe that should that be inequality? It's a good question. Yeah. Yeah, we can look at that later if we have time.
You did say approximately separate over inputs.
Yeah. So I think the approximation is this thing, right? So J to JD. So JD is essentially on these subnetworks. And the approximation here is that, okay, so J has like these blocks that are like subnetwork by subnetwork. And so this JD thing is kind of like block diagonal, right? So we only look at the within subnetwork Jacobians and not at the between subnetwork kind of correlations. And as I said, like essentially the assumption is like between the subnetworks that look at different features, maybe there shouldn't be too much covariance, so then we don't care about that. Exactly. So that's and so this like should be kind of a lower bound, if you will, because you're just taking stuff out of the matrix. Cool. And so the third thing that I'm also going to use is that we can actually use these precision or covariance matrices we get to estimate how much the different features interact. So if you remember the very last layer, where we add up all the different subnetworks, on these particular weights, we can ask ourselves, like on the last layer weights, like how much covariance is there between the different subnetwork weights. And if one subnetwork is always predicting kind of something, then there's another one correlated with that. That should give us an estimate for how much the different features actually interact and for how crude our approximation of additivity is in the end, right? And so for some of the features, maybe they interact so strongly that the additivity assumption is too strong, and then maybe we want to add a pairwise interaction back into the model. And I'm going to show that actually helps the performance in that case. Cool. So this was the Matthew slide. Now we're just looking at nice figures from here on. So this is kind of now simple toy data to showcase what I'm talking about. So here we have different synthetic features that are actually truly additive. So this is fully additive data, so the model assumption holds. And the interesting thing here that we want to showcase mostly is that we have one feature that is just noise. So this feature really has absolutely no predictive effect on the label. And if you use something like a generalized additive model or this neural additive model, which is the one we're mainly comparing to in this work, it kind of roughly tries to fit the constant zero function, but you see it hovers around it, right? And so for most data points, it's not going to be exactly zero. And especially if you might move out of the domain of the training data, you have absolutely no guarantee that it will be zero. And so our model, which is this one, has the nice property that because of this marginal likelihood model selection, it can fully recover like a zero function. It essentially realizes that this feature is useless, and it just regularizes away the whole subnetwork that is responsible for that feature. And this is very similar to what you would get in an additive GP model. Right? So an Oak GP was a paper that's actually also not that long ago, which is essentially doing this additive modeling with GPs, and they also have this marginal likelihood model selection, so they can also regularize this. So what we're trying to argue in our paper is essentially we get a bit of the best of both worlds between the kind of neural network modeling for like, kind of more complex data, but also we get this nice effect that the GP gives you, which is this marginal likelihood selection of features. So this is toy data. Now, what's more interesting is if we look at real medical data. So MIMIC3 is one of these big public data sets for ICU, so intensive care unit patients. So you have time series of patients on the intensive care unit. You measure blood pressure, heart rate, all kinds of things, and you want to predict whether the patient survives, right? So this is a mortality prediction task. And we see that both of the Bayesian models, so the GP and ours, get a better performance than the standard neural additive model. So this already shows you that there's a certain amount of uncertainty in this real medical data that is valuable to model. And if we go to a bigger data set, so hybrid is similar to MIMIC but much bigger, then the GP in our case doesn't scale anymore. So this runs out of RAM on the machine we use, so we can't use it. But our model still scales because of the neural network component that is much easier to scale than the GP. And so we again try to make this point that we get a bit of this best of both worlds, like we get the nice uncertainties from the GP, but also the scalability of the neural network here. Now I told you we can use the approximate covariance between features to add feature interactions back into the model, and that's what we did here. So our subscript 10 version of the model has 10 pairwise feature interactions added back in. These are the ones that have the largest approximate covariance. And we see that improves the performance of our model a little bit, at least on MIMIC. And interestingly, the Oak GP from their paper also has a version that adds interactions back in. They can't just do that for a subset, like they have to add all the interactions back in because of the way that their kernel is written down. So this is essentially using a different kernel than this one, and this kernel has all the interactions in there. And interestingly, like with this interacting kernel, we actually, in our experiments at least, get a worse performance. And you can wonder why that is. Might be because of the marginal likelihood having way more parameters to fit in the kernel now, so maybe that's overfitting to some extent. But yeah, at least in our experiments, like our interacting model seems to be the best one out of these ones. And this actually gets relatively close to the light GBM, which is somewhat of a relatively state-of-the-art gradient boosted model that takes all the full interactions into account, right? So this is not an additive model, like this is one of those that looks at all the interactions. And you can see by even just adding 10 pairwise interactions, we get essentially to that level, but still having the interpretability of mostly being additive in most of the features. So what does this interpretability look like? So if we compare again to the normal neural additive model, we see that our curves are much smoother. That's again an effect of this much likelihood model selection that kind of essentially makes the model less complex, or just chooses the complexity that's just needed to explain the data, but not more. And if you have any intuition for medical stuff, so maybe temperature is a good parameter to look at, right? You probably can imagine that having a body temperature around 37 Celsius is quite good, so you have a low mortality risk. If your body gets very hot or very cold, that's bad, so you have a larger risk. We also see in the background here the actual data distribution of the histogram, so most people are luckily in the healthy range. And you also see that if we move further out, we get more uncertainty in this, right? Because we just haven't seen that many patients in the data set. Now, one interesting thing that you see here is that our model has decided to completely ignore the bicarbonate feature. So you might wonder why that is, right? Is bicarbonate generally like just an uninteresting feature? We also didn't understand this, so we had to look a bit into it. And it turns out that in this particular data set, there are 3 features which are called sodium, bicarbonate, and anion gap. And the anion gap feature is just the difference between these two. Right? So these features are essentially like living in some 2-dimensional space, right, where this feature is kind of collinear with the others, which is why the model has decided to just ignore one of them. Like, it's kind of a bit arbitrary, but if you remove the anion gap feature and retrain the model, you see that it starts to look at this one now, right? So this kind of information is essentially mirrored in this feature now. And this shows you that really, like in real world data, the model can recognize if some features are uninteresting or uninformative. To look a bit again at how we do the feature interactions, here are again like a lot of the features we have in this medical data, and these are the posterior correlations that we estimate, right? And you see there's like a few of them that have very dark colors, so these are the kind of ones that actually strongly interact, and that's the ones that we will ultimately add to the model, while most of them don't really interact. So you see the additivity assumption is actually not as bad as you might have feared. Like, it could be that everything would be kind of blue and red and then would be a very bad model, but for most of the features, like, there's not that much interaction. So that's also presumably why the model works quite similarly to the light GBM baseline. And for our pairwise interactions, we can still plot these curves. Right now they're kind of 3D curves, so you have to have the color dimension as a third dimension. But you can still see how these things change, and as a doctor, presumably still have an opinion on whether you think that's the right behavior or not. And again, you get some uncertainty around this. Cool. So this is all now global interpretations, right? All these curves on how the whole model works. So this is good. Like, that's the first step, right? To show these to a doctor, and then if the doctor says, okay, I think that makes sense, seems to be a sensible model, then you can deploy the model, use it hopefully in a hospital or somewhere. But then if a new patient comes in, you might ask, okay, for this particular patient, like, why did the model make a certain prediction? And so that's the kind of local interpretation for a given data point. And again, because it's an additive model, you can just look at the components of every single feature, how they contribute to the prediction, right? And so you will see some of the features will essentially bias the prediction towards a positive mortality risk, right? So like, these features are essentially making it seem like the patient should be more at risk, while the other ones are less, right? So typically you could say age is your negative factor, so presumably this patient was relatively young, but despite the young age, had like some unfortunate, blood pressure and whatever, and these kind of scores. Now this is for the standard neural additive model. You see there's a lot of features that have a relatively small impact. And what we can do in our model, because we have these uncertainties around it, right? We can have credible intervals, which we here plot in these shaded colors. And what we can do for the interpretability is to say if our credible interval actually overlaps with 0, we just don't plot the feature because it's not clear that it actually has any strong influence, right? And so that means the list of features that people or like doctors, practitioners that use the model have to look at gets actually much shorter here. Okay, so this is another kind of argument why we believe that this type of model is more interpretable in practice.
The y-axis seems different.
Yeah, that's a good point. So I guess I don't know exactly why that is. So this is 2, right? So 2 is here. So you have like 3 features that are above this, right? And here not. Yeah, I mean, ultimately, I guess that might also be due to the regularization, right? That the model is a bit encouraged to not put too much weight on any given single feature. Again, like these are different training runs of the model, so there might also be some noise in how much decides which. Yeah, interesting remark. Cool. So just to summarize this part of the talk, the main point, like in a wider sense, that I'm trying to make is that if we have these very constrained model classes, right, which are often useful for interpretability, we can eke out a bit more performance within these model classes by being Bayesian about the methods in general. Cool. Should I take questions now or at the end? What's the usual? Anyone has questions for this part of the talk?
Discussion is always encouraged. That's why we
always encouraged. Great. That's a question. Right on.
So the thing I was going to ask about, so you've got something that's additive invariance, which to me actually seems like a bit of a problem, because say if things, so you've got something here where it's additive invariance, which seems problematic, because if every feature was independent and let's say Gaussian, it would be precisions that would add up variances. So do you see any issues that come in with the fact that you're being additive kind of almost the wrong way?
Yeah, that's an interesting question. So what you're saying is like if this were like a generative model, right, where you kind of try to generate new features or something, and each feature would be Bayesian and it should be additive in the precision. In our case, they're kind of additive in the variance, right? So I think in this particular predictive sense, I would argue that for the kind of interpretability, it makes sense to ask the question, like if we have one data point and we have a certain uncertainty about that, what's the contribution to the uncertainty from the different features, right? So this.
But if it's an observation, it'd be how much is it explained by this feature, and if it's how much is it explained, it'd be precision, because it would be once I know this feature, I want you know it as well. How much more, like the information sort of perspective explaining it's quite clearly.
Yeah.
The how is it explained by this, and so forth.
Yeah. No, I see your point. I think we can probably talk about that more offline. But in general, for the use case that we have here, I would argue that it still kind of serves a purpose to have these additive variances. But I can totally see the argument that in a general case, like mathematically speaking, like maybe having additive precisions would be more elegant or would like serve our intuition more about what the generative process might be, right? I wonder, I mean, this obviously also comes out of the kind of linearization of the model, right? So in the generalized nonlinear model, like that wouldn't be the case. I don't know if that makes a difference here.
I agree it's still useful though.
Yeah. But no, it's a good question, I think.
I had a question about the comparisons with the additive GP model. So I guess the main point of the oak GP method is the orthogonality constraint they put on the additive parts to make sure that each additive component is, I don't know the word, identifiable, maybe it might be a good word, because you could always just skew one of the components and then you can compensate on the other one that's actually not a true effect. Could you discuss a little bit if this was a problem in your model or not?
Yeah, that's also a good question. So I think essentially we don't have an explicit orthogonality constraint in that sense. I guess what in our model makes it maybe more identifiable-ish is that because of the marginal likelihood that gives you like some general regularization on the size of these weights and stuff, like you generally don't have an incentive scale things up and down and make the model complicated, right? So the least complex allocation, shall I say, of responsibility to the different features is going to be the one that's selected for. But then, of course, like there's still cases where this is not identifiable, and I guess one of them was this case here, right? So like in this particular case, the model could have decided to ignore any of those 3 features and just keep the other 2, and ultimately it's a bit random. And if you retrain it, so this is like one training run, right? If you retrain it, it actually happens that it would ignore like sometimes the other features. So yeah, to some degree, this is not a unique solution, but I guess in real life, that's just what it is, right? Like if you have 3 features in this sense, for instance, that are collinear, like in the data, there's not much you can do about it, right? There's not one true solution that says like, oh, it definitely has to be the bicarbonate that's zeroed out. Like it could be any of them, and each of these would be equally valid, I guess.
But also like 2 mics there, if you guys dare feel, not included. So we have 30 more minutes.
Yeah, cool. I'm already running behind time. Okay, cool. I'll try to move a bit more quickly through the next thing. So the next part is going to be about computational efficiency. And particularly, I want to talk about neural network sparsification and about this paper, which I think has a very cool title, Shaving Weights with Occam's Razor. I was mostly work with people at TU Munich, but also with Alex again. And the idea is that if you have a neural network, right, with a lot of parameters, there's this idea that you can sometimes remove parameters without hurting the performance too much, right? And that's sparsification or pruning. And there's 2 types. There's the unstructured pruning, where you just remove weights wherever you want. And there's the structured pruning, where you actually remove entire neurons or like units, essentially, right? Which means removing entire rows or columns from your weight matrices. So the unstructured pruning is a bit of the easier use case, so this is what we're going to talk about first. But it's a bit harder to convert this into actual computational savings, right? So like if you have unstructured pruning, you still have weight matrices of the same rank typically, they just have more zeros in there. Well, if you have structured pruning, you actually get smaller matrices, so you can really speed up the computation. And so a lot of the literature of pruning has focused on pruning criteria, right? So this assumes you have a trained neural network, and now you want to decide which of these weights to remove. And that's a very useful literature. But what we're trying to do here is to say, let's kind of take a step back almost and ask ourselves, like, how should we train the model such that then we can prune it better, right? So this is what we call sparsifiability. So can we train models such that they actually use fewer parameters effectively, so that there's more parameters that we can actually remove afterwards, kind of regardless of which pruning criterion we use. And so the idea, the way we do it is, that might now not come as a surprise, is we use again a kind of Laplace marginal likelihood type of approach. And the idea is, again, with this like Laplace marginal likelihood training, we encourage the model to learn the kind of simplest model that still explains the data. And in this case, simplicity, if you choose the right prior, means to use the smallest number of different parameters in some sense. There's some technical questions about whether you want to use a diagonal Laplace approximation or a chronic or factored one. Never mind that. And then what you get is a certain weight matrix that might have some larger and some smaller weights. And then you ultimately use a pruning criterion. So as I said, you can use any pruning criterion, but one that we kind of propose to use because it's relatively nicely reusing some of our Laplace computations is to just take the magnitude of the weight, or the squared magnitude of the weight, times the posterior precision, right? So that essentially comes from the fact that we already had to compute the posterior precision for our Laplace approximation, so we have that anyway. And then what the score measures is essentially how big is the weight compared to like how uncertain it is. So it's something like a z-score kind of thing, right? So it's like how significantly different from 0 is this weight essentially. But again, if you want, you can use any other criterion. We're just saying this one is very cheap, and we're going to show that it's going to work about as well as the other criteria that are more expensive that use like fancier math. And then, yeah, you have to decide whether you want to do unstructured pruning, which is just removing some weights, or doing structured pruning, where, as I said, you remove like entire columns. And then if you do structured pruning, you obviously have to aggregate the score over the structure, right? So if you have a whole like neuron, you have to sum up the scores over all the incoming and outgoing weights to then decide whether you want to remove the neuron. And I'm going to show them that this actually works quite well.
Yeah, you're removing neurons, so like all the weights are gone? Is that how you do it?
Yeah. Yeah, so essentially like what this is doing is kind of summing over like rows or columns of the weight matrix, right? Cool. So this is maybe the most like busy figure, but essentially what it should show you is, like we have 6 different types of networks and data sets, from like fully connected networks on some cancer data to, like nice little small CNNs to ResNets, white ResNets, vision transformers, and this is a language model kind of thing. And the rough shape of these curves is always the same, right? So like the idea is you start with a model that has most of its weights, and then you prune, right? So this is kind of the percentage of weights pruned away. At 100, you don't have any weights left, so this shouldn't work anymore. But what we see is we can prune quite a lot of weights, right? In some cases, up to 90% or more, without losing much performance, right? And typically, between all these weird colors that we're comparing here is all the solid lines are using our method, which we call SPAM. So that's like sparsifiability with the marginal likelihood. And so what you should see is that the solid lines are the ones that get you the most performance at the higher sparsity levels, right? Where all the dotted lines, they have more of this natural falling off shape that you might expect, where if you remove parameters, like it gets worse and worse and worse because some of these parameters are useful. First, you remove the ones that are maybe a little bit less used, so you just have a small decrease in performance, and later you remove the important ones. But if you train with this marginal likelihood that we propose, you actually have a large number of parameters that are really essentially not used by the model, and you can just remove them without any custom performance. And then at the very end, you get like the parameters that the model actually uses, and removing them really gives you a very steep decrease in performance. So this is kind of essentially what we're expecting to see, and we see that for different criteria, right? So the different colors here are different pruning criteria. Some of them are very simple, like magnitude pruning. Some of them are fancy, like RASP and SNP, which use some kind of, gradient-based information theory stuff. And ours is this OPD, which is just, as I said, using this pre-computed posterior precision that we have lying around anyway. And we see that that really works quite well, right? So the light blue curve is essentially, in most cases, not worse than any of the other pruning criteria, so you can get away using these like cheap computations that we've already done. Now this also, interestingly, is the same for the uncertainty estimates, so this is just now lower is better, so that's why the curves look the other way around. But again, we see the same shape, and we see the best performance at high sparsities. One interesting thing that you see here, which is what I want to use as a tiny little tangent on why I think the ECE is a bad criterion, right? So this is an expected calibration error. And you see the best ECE is actually achieved at high sparsities by random pruning. So this is the purple curve. But you might not see from these figures that this is essentially just doing random guessing, right? So this is at 10% because for MNIST and CFAR and so on, like we have 10 classes. So this is just random guessing, and if you just do random guessing for all the points, you get a perfect ECE calibration, because like then you always have 10% accuracy and 10% confidence, and that fits. But this is why this criterion is a little bit less nice to use than, let's say, the Breyer score or the NLL, which are both proper scoring rules, so they have a much more well-behaved calibration at large sparsities. Okay, so this was all unstructured pruning. So as I told you, this is kind of the easier way to do things, but it's also the slightly less useful one because you don't actually get computational benefits. So what we then did is to do structured pruning, and here we also see the curves aren't quite as nice and steep anymore, because if you do structured pruning, it's a slightly more brutal intervention on the network. So you expect that you lose a bit more performance. But again, our curves, the solid ones, are typically the ones that give you better accuracy. And in this case, also our criterion, the light blue one, is actually better than a lot of the other pruning criteria. So this was quite encouraging to see. And now, because structural pruning really gives you benefits in computational aspects, instead of just plotting the actual sparsity as we do here, we can plot essentially the same curves in terms of real like flops. So this is like compute time or size, like so memory on disk. And you see, especially if you go to the higher levels, so now the x-axis is inverted, right? Because now smaller size and smaller compute time means higher sparsities. So at the higher sparsity levels here, where we have like very small number of flops or small disk size, we see that with our criterion, we get the smallest decrease in test accuracies. We get the best accuracies of all the models. And this can now really, like if you get to a model that's just, kind of 10 kilobytes, you can really run this on like edge devices now, right? So if you want to build a toaster that has a little like CNN built-in that can tell you whether your toast is right or whatever, like this is now really the realm where these models can be made to work. Cool. So the key message is we can use Bayesian model selection with a marginal likelihood to improve sparsifiability, and then yield kind of networks that you can prune more easily with like any pruning criterion really. But then we also have this nice posterior-based pruning criterion, which is relatively cheap to use and works quite well in practice. Any questions for this part?
So thanks for that. I was wondering, is there a way to figure out whether or not you should prune at all? Like, because the examples you were showing, I guess they were like massively overparameterized networks on quite simple data sets, right? So by definition, you have the intuition that 80% of it is prunable. But like, if you go to more complex scenarios, it's likely that a lot of models like you cannot even prune whatsoever. So is there like something in your criterion that would tell you, like, don't even start to prune, or only prune like 1% and then stop? Or do you always have to go through like the curve and do some cross-validation kind of thing to figure that out?
Yeah, that's a good question. I think so. To some extent, you could wonder whether the actual absolute value of these criteria is transferable between models, and I'm not sure that's something we've tested, but I agree it's a very, very good question to test, right? So if we would know from whatever fashion M is, like what's the value of the pruning criterion at 80% accuracy, could we use that as a value to then transfer to CFAR and still get a good accuracy or something, right? This is more or less what you're asking. I suppose, like if we,
I mean, I guess so, but I was less thinking of like the absolute performances, and rather like when you go back to your slide on like the metrics themselves we use, and like the, like in the past, the plasma approximation and so on.
I see,
to get like a signal from there. At least that was my intuition.
Yeah, I mean, you get kind of, you just compute a score for every parameter, right, and then you get a ranking. And I mean, the way that these curves are then made is like we just go through the rank weights and we remove them one by one, more or less. I mean, maybe
so it's normalized, right? So it's like, or it's not. Like the score is normalized?
So the score is just this, right? So it's just the parameter magnitude times the precision. And then you can wonder, like, I mean, to some extent, that should be kind of following some Gaussian. So like I guess it gives you like some, if you want like something akin to a p-value of like how significant that weight is. So in that sense, it's comparable, but I guess what I don't know, and like what is a good question, is like if we have a score that's, kind of 95% like p-value or whatever we want to call this, is that going to be the same between two networks on different data sets? Like, does it have the same effect on the accuracy or not? So I don't know that, but I think that would be a good thing to say.
Yeah, so I don't want to shamelessly plug myself. Maybe we can talk offline. We should on the inverse question, like when to add if you have insufficient.
Oh, okay, cool. Yeah, nice. Yeah, thanks for the question.
Please shamelessly plug yourself. This is why we're here.
No, it works, I think.
I also have a quick question. What are you optimizing the marginal likelihood with respect to? Is it the weight decay or?
Yeah, that's also a good question. So we're optimizing the parameters of the prior, and indeed, like in our particular work here, we have typically like Gaussian priors. So then we optimize the prior variance for each weight.
And this is during training?
Yeah, that's during training, yeah.
And do you have the intuition why optimizing this during training improves the classifiability of the work?
Yeah, so I suppose like my intuition, so the way that works is we're using the kind of, now this is harkening back to like this ICML paper that we had in 2021 where we did this marginal likelihood Laplace thing. And so the approach is usually you kind of train the network for one epoch, like normal SGD or whatever. And then after that one epoch, you make one step on your marginal likelihood kind of meta objective. You change the prior, and then you optimize for another epoch, and you do this like iteratively, right? So the intuition in some sense is you kind of train the network for an epoch, then you see which weights at this point are like more important and less important, and then the marginal likelihood will tell you, oh, the less important weights, you can actually kind of increase the prior precision because we don't care. And the other ones, like we should be more sure about. And then you have another epoch where now like this kind of reinforces to say, okay, the weights that were important in the first epoch, like maybe they're still important, the other ones maybe less. And then essentially over each epoch, there should be kind of convergence towards using some of the weights more and more and some of the weights less. And then that would be my intuition, what actually happens. Yeah.
Okay, so you have a right precision for each weight, so it's like a diagram.
Yeah, you can. So this is the kind of unstructured pruning idea. If you want to do the structured pruning, so that's actually an interesting question if you bring it up. If you want to do the structured pruning, of course you can say, because we aggregate over these structures anyway, and we know what they are, right? Like the rows and columns of the weight matrix. We can also define the prior in a way that they have shared variance across those structures, right? So that's actually something we do in practice.
No. Just want to say that coffee room number 2 is open. So, but the speaker is very interesting, so don't really.
Cool. I will just give you a whirlwind of the last thing. So this is just saying, like if we have big foundation models and we do this fine tuning usually, right? So you pre-train on some data set and you fine tune on another. Like this sounds a bit like you're updating your beliefs, right? And so like we know how to update beliefs. You should be Bayesian about this. So can we be Bayesian about this whole fine tuning thing? So there's a little bit of some stuff we've been doing in this direction very recently. So just one paper I want to show is with a few students of mine at Helmholtz, where we did essentially this kind of swag method for LoRa. So LoRa is this idea that if you fine-tune a language model, you don't want to fine-tune the whole set of all the parameters because that's going to be a lot of work. So what you do is instead you add these low-rank extra parameters, right? So you have this big pre-trained weight matrix that's very large, and now you have like a very small little low-rank extra weight matrix. And so this is how a lot of people in practice actually fine-tune language models. So as a kind of rough idea of what this means is if you have like GPT with like 100 billion weights, then maybe your LoRa parameters are going to be on the order of 10 million weights, right? So it's kind of roughly 10,000 times less compute. And so we were saying, okay, like if we do the fine tuning in this LoRa subspace, can we be Bayesian in this, right? So we thought, oh, maybe we can do Laplace. But obviously it was a very straightforward idea, and Lawrence said it also, and he was faster than us, so he wrote this nice paper. So great, Laplace LoRa works, so we were like, oh, okay, we're going to do something else. So we did swag LoRa, which is like the kind of cheap version of Laplace, so like not actual Hessian computation, but we just essentially go into this LoRa subspace, and we run our little SGD, and then we use the SGD iterates to kind of empirically compute first a mean, which is going to be our posterior mean, and then a covariance, which is based on the empirical covariance of the iterates. So this also gives you Gaussian similar to Laplace, just a different way, and we show that this actually in practice also works quite well. In some of the tasks, it works actually better than Laplace in terms of accuracy and also like in terms of likelihood, so the uncertainties you get on some tasks, especially question answering tasks, they're a bit better than the Laplace. Cool. So another paper that I'm really going to brush over is that we did the same idea with this LoRa fine-tuning, but for vision models. And in vision models is interesting because the LoRa thing that I showed you here is essentially designed for fully connected matrices, right? So this is just a normal matrix, and this is now a low-rank matrix. But in vision models, especially in CNNs, you have these convolutional things, and they are kind of higher order tensors, right? So typically you might have something like a three-dimensional tensor. So instead of just flattening this and pretending it's a fully connected layer and doing LoRa, you can actually be a bit smarter by using this so-called Tucker decomposition. And so you can decompose it into like 3 low-rank vectors in this sense, and then you have a small actual 3D vector, and then you have these lower dimensional outer vectors that you do outer products with. And so essentially what we show in this paper is that if you do this kind of slightly smarter decomposition, which we now call co-LoRa, so convolutional kind of LoRa, you get a nicer scaling. So essentially what you see on these plots is the dotted or dashed line is the kind of baseline model that we're fine-tuning. If you would do full fine-tuning on all parameters, you would get the best performance, that's here in blue. And if you do LoRa naively, you get kind of a model that improves over the baseline, but not as much as you would like, right? And if you do this co-LoRa thing, the green one, you actually get a nice interpolation on this line, essentially between the untuned model and the fully fine-tuned, so you can really trade off how much compute you want to spend, how many parameters you want to fine-tune, and you get essentially a kind of proportional increase in performance for this. Cool. So yeah, sorry for being a bit quick about this part, but feel free to ask me later about the details. So the key message is just that if you do this inference in these low-rank subspaces like LoRa, co-LoRa, you can actually effectively endow these foundation models with Bayesian update capabilities. If you want to learn more about BNNs, because now you're like all interested in using them, we wrote this little review paper together with Julien, who's not here right now, but might join later, I guess. We also have this cool position paper that we're going to present at ICML with a lot of people, including some of them are here today, where we argue that Bayesian deep learning is really needed in this age of large-scale AI, and that is essentially making all these arguments I made in this talk, but a bit more carefully and nicely. So if you're half convinced by what I said, like please read this paper, and then hopefully you'll be fully convinced. And another position paper that I'm also going to plug while I'm at it, which is on generative AI more broadly, but also has a lot of Bayesian stuff in there. So go ahead and also read that. So with that, I'll conclude. Hopefully I've shown you that in this age of foundation models, there's still a lot of open questions, particularly in these areas of interpretability, computational efficiency, and uncertainty and belief updating, and that we can make some headway if we, think back to our Bayesian foundational principles and try to build them into these models. And yeah, essentially I showed you these 3 things that I'm not going to read out again. So yeah, please go and have some coffee, and thanks for indulging me for so long.
Thanks, Bob. The gist of this session, the coffee and the question answer sessions are overlapping, so don't feel guilty if you have to get up and go to coffee. It's important, but if you have questions, it's also. Anybody has questions? I have questions. I feel like at least the first 2, maybe even the third one, but the first 2 seem to be about perturbation. Is that? Do you agree with that? Or the questions that we're asking about additive models, where you sort of specific structure and you try to understand how each feature contributes to the overall thing. And the second one where you're pruning, which is sort of going from a trained model to a model that's sparsified, and you're trying to find directions where things don't change much. Does that make sense?
Yeah, no, I think that's one way of looking at it. Yeah, probably. I mean, for the pruning, I can see that that's really a very natural way of looking at it. For the additive models, you can phrase it in different ways, but it's certainly one valid way of thinking.
I see. Yeah, but so when you use marginal likelihood to do these things, and then I wonder why, how this is related to other things. So like the paper by Lacoon in the 80s, right, the optimal brain damage or something, and there he's using Hessian, and then here you're using precision. Right? I don't know. Did you discuss any relationship with that kind of method?
Yeah, definitely. I kind of briefly skipped over this, but so the reason why this is called OPD is because we call it optimal posterior damage, which is a kind of little nod towards the optimal brain damage. So essentially, like the main difference is that where we have the posterior precision, essentially in Jan's original paper, they have the Hessian of the likelihood, right? So the main difference is like we have the Hessian of the likelihood plus the Hessian of the prior that we use here, and they don't use the prior. So this is kind of the main difference.
Do they also have the theta square?
Yeah, they also have the same theta square. Yeah, so their paper is likelihood Hessian times theta square. And so the only difference is that we have the prior in here.
If nobody has a question, I'll keep short. Yeah, you can just go to the mic.
So yeah, actually I had a short question about the sparsity. In light of maybe it's already old research these days, but I was thinking about the lottery ticket hypothesis, right? The idea that there is some weights that you can prune and you can still fine-tune the natural factorial. Do you think using this sort of Bayesian pruning might also be able to find ways that we can fine-tune natural? Thinking especially in light of the other topics.
Yeah. Yeah, that's a very good question. So I'm not a huge expert on lottery tickets. I think my intuition would be, and maybe you can tell me whether you agree or whether it's wrong, is that in the standard lottery ticket thing, you have a neural network and you initialize the weights in a certain way. And this initialization, in some sense, defines what the lottery ticket is, right? So like my vague understanding is that some of the weights inside this big network will have been randomly initialized to already be very close to what they should be to solve the problem. So during training, these weights will just converge faster and they will end up being kind of the winning ticket that actually solves your problem, while the weights that will have randomly been wrongly initialized will not solve the problem, right? So that means that essentially if you have a big network and you reinitialize it several times, you will get different lottery tickets, is that right? So I think what we do here is a bit different in that sense, because we want to train the network in such a way that we have a posterior distribution in the end that actually also has good likelihoods, right? That's why we show the log likelihoods and everything. So in my understanding, if we have a Bayesian neural network where we sample weights from the posterior, like probably every posterior sample would have different lottery tickets in there, right? So then you have like kind of a distribution over different lottery tickets, whereas I guess what we want to have is a version of a lottery ticket where like if you fix those parameters, right, so if you remove the other ones, if you just keep the subset, then within the posterior over those weights, you have a useful predictive, right? So this is, I mean, again, along the lines of saying like we can capture the posterior predictive uncertainty that we need within a subset of the parameters, and a lot of people work on similar things, and I think Tom's going to talk about that more also. But yeah, I think from that point of view is maybe a bit different from the lottery ticket idea, where you really have parameters that aren't privileged a priori by virtue of being in the right part of the network, but are just happen to have been initialized by lucky draw somehow, right?
Yeah, a bit of apologies. Yeah, that makes sense. But what I was mostly thinking is, I mean, in their original argument that those weights would be the best fine-tune afterwards compared to other classification methods where you cannot fine-tune it. So the question was more like, is it feasible to fine-tune your sparsified?
Oh, I see. Okay. No, I think that should be feasible. Yeah, that's maybe the short answer. Yeah.
Thank you. So I have a question about the second one. So in Bayesian pruning literature, people have been considering other priors, like priors other than Gaussians, which are more sparsely prone. So I wonder if those plots approximation or minor likelihood is still available for those class of priors, but have you considered using other sparsity using priors?
Yeah, no, that's a very good question. So yeah, that's maybe a bit of one of the kind of downsides of the Laplace approach that I've been brushing a bit under the rug. But like, of course, in order to compute these Hessians, you need a prior that has well-defined like nice second derivatives, right? So like with the Gaussian part, it works well. If you have something like a Laplace distribution prior, for instance, that wouldn't work anymore because like then you don't have this. Essentially, your second derivative is just going to be zero everywhere or undefined. And yeah, for some sparsity-inducing distributions, it's even harder. Like what people often do is these kind of spike and slab priors. Like then you essentially don't have derivatives in any meaningful way anywhere. Or you have these horseshoe priors, which have like Cauchy tails, and then you run into like other numerical issues. So like for a lot of priors, like getting a nice Hessian that's going to be positive, definite, and like work for numerical reasons is challenging. So that's why we did the kind of Gaussian thing. But I think it would be an interesting question to ask: can we find other prior distributions that have some of these properties that you talk about, like that are more sparsity-inducing, but still work well in the Laplace approximation framework? And so we haven't looked into this, but I think it would be an interesting research direction.
I think I have seen a paper using truncated normal distribution or normal distribution. I haven't done the calculation, but I believe for those variations in Gaussians, slightly different from just Gaussian, but still more computationally tractable, and maybe we can be able to come up with approximation for the marginal likelihood, and those kind of priors are still sparsely found.
Yeah, for sure. I think that's a good intuition. So probably like I agree. Like if I would have to come up with like the simplest prior that's sparsity-inducing and more interesting than this one, is probably like a mixture of two Gaussians, right? Where you have like both Gaussians are still centered at zero, but like with different variances, and then you get like a more peaked distribution around zero. But you can essentially do everything we do here. You just do it twice for the two Gaussians and get them.
Thank you.
Yeah. Thanks.
All right, great. So, in the interest of time, we should thank the speaker for the wonderful talk.
Thank you.
We have our second talk. It's my pleasure to have Professor Juho Lee, who is an associate professor in KAIST in Korea, so very close by. He earned his PhD from Posttech, also in Korea. Yeah. And did his postdoc in Oxford in the computational statistics and machine learning group. I suppose you were with François Caron.
Yeah.
François is a really old friend of mine. I'm very happy to have you here. Your research is focused on Bayesian deep learning with contributions to Bayesian non-parametrics, meta learning, and generative model. Yeah, and Juho is another, I think I shouldn't use the word young, but I've got in trouble with that, but let me say young in that sense, that new person coming and doing lots of amazing things in the Bayesian world and deep learning world. And I got to meet him earlier this year. I'm very happy that you could make it back here. So looking forward to your talk.
Thank you. Thank you for the introduction. I'm both honored and excited to be here. And thanks, MT, for generously inviting me. So today I'd like to talk about the recent works in our research group, and I titled my talk to be toward scalable and generalizable Bayesian deep learning. So I hope that this title is not really like an overselling of our works. I will try to make it as close as possible to the content I'm actually trying to present today. So when I have to talk about these kind of things for instance, in Korea, I usually have to devote like more than 10 minutes to persuade the listeners why we should do Bayesian deep learning or Bayesian inference from the first place. And it's here to say I don't really have to do that because I think you all agree with the necessities of the Bayesian paradigm. So I can probably summarize the standard process in Bayesian inference or Bayesian deep learning, Bayesian deep learning more specifically. So given a data, we choose a model. So in our case, we are doing Bayesian deep learning. We are interested in doing these kind of things with deep neural networks, having like high-dimensional parameters there. And then we choose our modeling assumptions, like choosing a prior and a likelihood And then given those selections, we infer the posterior distributions given the training data. And then after we have inferred the posteriors in some way, then we can compute the predictive distributions for any test function H. So there are several challenges in this process, especially in Bayesian deep learning models. So first, choosing a proper prior. So for mostly in computational region or historical region, we tend to use like Gaussian prior or a slight variations of Gaussian prior, but we still have a question whether the zero mean Gaussian prior over the weights of the neural net is the good choice. So, I mean, in some sense, it isn't even clear whether we should play on the weight space for placing our prior distributions. So should we work on weight space, function space, or something else? Should we work like the hybrids of the weight space or function space approaches? All those questions are still unanswered. And of course, the inferring the posterior part. I mean, Bayesian deep learning or not inferring the posterior of the given model is just a difficult problem, right? But when it comes to deep learning, especially we are typically working with really high dimensional models and working with like large scale data doing this inference is more extremely challenging problem. And even if we have somehow done the posterior inference, when we are computing the predictive distributions, we also face the challenge, especially approximating the predictive distributions is a hard problem. And the typical way of doing this is, of course, the Monte Carlo approximation, but in order to do the Monte Carlo approximation, you have to compute the forward passes through your neural net multiple times, right, with different parameters. And this might have been a simple solution for like relatively cheap models, but when it comes to a large deep neural net, especially say you want to do this for language models, doing the forward passes through those language models like 10 or 20 times, that is already a bottleneck. So we face another challenge of inference cost in this Bayesian deep learning story. So today I'd like to present some solutions that our research group is pursuing for each of these challenges. So for choosing a prior, so I will try to introduce a way of building a prior distribution out of a pre-trained model. Like if you have a large pre-trained model, how could you leverage that pre-trained model to turn it into an informative prior that you can train with? And also, I'd like to present our recent work on meta-learning stochastic processes that can be used as a prior distribution for generating tasks. And for the inferring the posterior part, I'd like to present our recent work about learning better MCMC algorithms in a data-driven way. And finally, for the computing the predictive part, I'd like to present our work on accelerating the Monte Carlo estimation using two different types of approaches. So the first one for the prior. So the first work I'd like to present is about Bayesian non-parametric way of doing transfer learning. So this is a joint work with my students and my former colleague. So to summarize, it is a Bayesian way of doing transfer learning from a pre-trained model. And the key ingredients in our work is that we use a flexible non-parametric learning scheme to build an adaptive prior that can quickly adapt to the distributional shifts in the downstream tasks. So the transfer learning is like a standard approach used in deep learning. So you have a large pre-trained model, like if you are working for image classification, you might have a classifier trained on ImageNet, and then you want to just fine-tune those ImageNet pre-trained classifier on your downstream classification tasks. So in transfer learning, what you typically do is you just bring the pre-trained parameter, and then you initialize your model with that parameter, and then fine-tune. So that is a typical transfer learning procedure. But the transfer learning for us, Bayesian, already feels like using a prior knowledge, right? So the pre-trained model itself can deliver generate prior knowledge that can be leveraged for various downstream tasks.
So our question here is that rather than just trying to just initialize your downstream model with the pre-trained prior, is there a better way to use the pre-trained model as a prior distribution? So there have been like several existing works on this direction. So the easiest one would of course be the naive transfer learning, where you just initialize a downstream model with the pre-trained weight data not. Another approach was like using a Gaussian prior but centered at the pre-trained weight. So it is like regularizing your downstream model, not deviate too much from the pre-trained weight. And more recent one was like rather than simply using a Gaussian prior, using a more elaborated prior like swag. So you do a swag on the pre-trained model to get a better center and covariance matrices for the prior, and then use it as a prior for the downstream task. So in our approach, what we do is rather than like just bring the pre-trained prior and then setting a prior around it, we choose to construct a non-parametric prior out of the pre-trained model. So not in the weight space. To do that, we use the learning paradigm called Bayesian non-parametric learning. So where we use the directionally processed prior on the data distribution and then use it to handle the shifts between the pre-trained data and the downstream data. So what I mean by Bayesian non-parametric learning is like we have a data set, and then we assume a class of parametric models F of data. Then we have a loss function of interest. So the loss function can be a generic loss function that you wish to optimize. But if you, for instance, select the loss function to be the likelihood of your low likelihood of your model, then you end up with minimizing the KL divergence between the true data distribution and the model distribution. So here in non-parametric Bayesian learning, what we do is that instead of choosing a prior distribution on the weight space, what we do is that we place some prior distribution on the data generating distribution. So we don't, of course, have an access to the true distribution, so we elicit a directionally processed prior for those data generating distribution, where that the F base is like a base distribution. So F base should be your initial guess about the data generating distribution, and then by the conjugacy, the data generating distribution after observing the real data down, in our case, in transfer learning, the data would be the downstream data. So due to the conjugacy, the posterior still is the directionally processed distributed, where now the posterior is a mixture of your base distribution plus the empirical observations. So you like somehow interpolate between the observed data and your historical prior choice. Then this distribution over the data distribution can naturally be pushed forward to the distribution over the prior. So given a sample from the distribution of the data distribution, you can solve the minimization problem of given the loss function, and the corresponding argmin parameter, which is a functional of the data distribution, becomes your posterior sample. So using these parameters, you can do the inference. So then we adapt this paradigm into the problem of problem of transfer learning. So we call this algorithm Bayesian non-parametric transfer learning. So the idea is, so given a pre-trained model, so which can be like image classifier or even like generative model. So what you do is you first, so here I'm assuming a classification task, but you can of course extend it to like regression or other type of supervised learning problem. So given a pre-trained model, what you first do is you do a linear probing on the downstream task. So which means that you just fix the feature extractor part of your pre-trained model and just learn the linear weight final classifier layer in this case. And then say you have that probed model, F probed. So we construct the base distribution, our historical knowledge about the data generating distribution, to be the one like in equation 6, which is basically our prior about this data pair, X and Y, is the Y being the predictions given by the pre-trained model. So this is so the prior, the role of this prior is similar to what you would be doing in the knowledge distillation. So in knowledge distillation, when you are distilling a large model into a smaller model, what you do is you try to deliver the predictions from the teacher model into the student model. So likewise, what we are saying is that the prior that you can get from your pre-trained model is like the responses from those pre-trained models when those downstream data has been fed into. So we, of course, have some technical contributions to make this posterior sampling more efficient, but I won't go into the detail.
What is the linear prop trained on a downstream task?
So it's like, say you have an ImageNet classifier pre-trained, and your downstream task is MNIST. So of course the dimensions are different here, but assuming they are just the same, and what you do is you just detach the linear classifier layer from the pre-trained model, and you just train the fresh linear classifier layer for the MNIST.
It's last layer.
Yeah, last layer retraining. So then, given this, under this non-parametric transfer learning framework, sampling for each parameter theta boils down to solving this problem of optimization, where you choose the weight for the population from the Juho-Lee distribution. So this is due to the truncation approximation of the Juho-Lee process. So you end up with minimizing the weighted optimization function with some regularization coming from the prior model. Yeah.
Assuming you're learning distribution itself is a future model, or are you learning just the weight parameters, point estimates?
So here, each optimization is a point estimate.
So the pre-trained model.
Pre-trained model is a point estimate, of course. So yeah. So if you have a look at the optimization problem, it is quite similar to the knowledge distillation actually. So we are learning from the downstream data, of course, but we are also learning from the teacher predictions. But we are controlling the balance between learning from the downstream data plus learning from the teacher. So how much should we distill from the teacher, and how much should we learn from the downstream data? So that is adaptively controlled by the Juho-Lee weight sampling. So here, as a result, the important hyperparameter we should tune would be the alpha, the concentration parameter in Juho-Lee process. So depending on the strength of alpha, the model will choose to whether or not to believe in the teacher too much. So the alpha should be fine-tuned using cross-validation, unfortunately, but we think that there should be a better, hopefully fully Bayesian way of treating the controlling alpha problem. But at least now we are doing the cross-validation on tuning the alpha. A good thing about this non-parametric Bayesian learning is that the sampling of each theta can be done in parallel. So unlike in MCMC, where you have to construct a Markov chain in order to collect multiple samples, you have to follow a trajectory. But here, just sampling procedure is an optimization problem, so you can do it in parallel. So run multiple optimization procedures on multiple machines, then you get multiple samples as a result.
Can I be a little bit annoying and ask you?
Yeah.
So compared to MCMC, I understand, but compared to neural network side, I don't see what is new, because it honestly seems like knowledge distillation.
Yeah.
Yeah. So what is
So unlike in knowledge distillation, so we have now the randomness in the data distribution. So it is also similar to what is happening in bootstrapping.
I see.
Yeah. So we are, and especially if you have a look at the weight part for the downstream data and the knowledge distillation part, they are from different hyperparameters of Juho-Lee distribution. So the strength of knowledge distillation is adaptively controlled by this Juho-Lee sampling procedure.
Okay, so where's the Bayesian part? Like something should be learned somehow that maybe these weights are adjusted accordingly. Something, maybe I'm missing that.
So the Bayesian part is, so we choose a prior, the data distribution F, and the posterior Bayesian part is due to the conjugacy. And if I push forward this posterior measure into to the parameter by equation 5, then
so would it be a bad thing to say that it's a reinterpretation of what people do there by looking at the conjugacy of this?
Yes.
Okay, thank you.
And you can also think of it as an ensemble of knowledge distribution, multiple knowledge distribution schemes with different controls over the prior strengths.
Makes sense. Thank you.
So of course we tested this on various models comparing to prior works on Bayesian way of doing transfer learning, and we do a lot better both in terms of accuracy and negative log likelihood, the uncertainty quantification. We also managed to do this for larger models like VIT or language models, and we get some significant improvements over the baselines. So I think this is a nicer. As MT pointed out, the resulting algorithm doesn't look like really complicated. It is somehow similar to the previous algorithm, but the point is that you are adaptively controlling the strengths of the knowledge station, and then you combine those multiple knowledge stations result into a single Bayesian fashion. So by doing that, we were managed to behave better, especially if you have a distributional shift between the pre-trained data and the downstream data, then the model will know that. So I have to believe less in the teacher model, so you can control the strengths of the, especially the hyperparameter alpha, so that you can do better in the downstream tasks, rather than just trying to solely believe in the pre-trained model. Okay, the second work is the recent work. So it is about learning stochastic processes out of data. So we proposed a novel neural process model that can generalize to data with arbitrary dimensions. So I will be more specific about what do I mean by arbitrary dimensions. So I believe this is an implicitly meta-learning stochastic processes in a data-driven way. So given data distribution, what is a good way to learn stochastic processes? So let me quickly summarize what a neural process is. So a neural process is a stochastic process defined with neural networks. So comparing, for instance, the popular stochastic process model, the GP regression versus neural process regression. So in GP, once we specify the kernel, then the predictive distribution is just given in closed form. So what you have to do is you adjust the hyperparameter by doing empirical Bayes or so, right? And in MP regression, what you now have is that given a data set and the curry point x star, the predicted distribution is just computed with these neural networks. So it is somehow a free form, but here interesting thing is that when you are encoding these given tasks, you have to encode the data set you are given. So you are encoding the training data given to you into some parameter latent variable, and then using that latent variable, you want to compute the predicted mean and variance of your query x star. So unlike GP regression, the parameters of these encoding and decoding networks are just randomly initialized, so you need some data to train those parameters. I mean, you need some experience to learn about this way of doing predictions. But in GP, we already know how to do the prediction, right, once you specify the kernel. So the neural process requires a meta-training stage where you have to train your model with sufficient number of data. But once trained, unlike GP, you can do the computation much faster. Like you don't have to do matrix inversion, for instance, and you don't have to do the empirical Bayes. So once you have trained your model sufficiently well, then you can quickly amortize the cost of doing inference and then just do a quick prediction. And a nice thing about MP is that if your data is like highly non-trivial, so that you are not sure which kernels should be used or something like that, or you are not sure whether the Gaussian assumption is right, MP is just a data-driven way of constructing stochastic processes. So it will, ideally, it will learn the most viable stochastic processes for this specific type of data. So people have been using MP as a showcase. People have been using MP to learn the stochastic processes of, like, for instance, the image completion problem. So you are given the pixels, the coordinates of the pixels, and the problem is to predict the intensities of the pixels corresponding to those coordinates. And also, you can also apply this MP model to, like, simulator solving the differential equations for the simulator. For instance, here I applied MP to learn the regression models for predator-prey model, and then show it can, like, indeed predict those solutions of the differential equations. But an apparent limitation of existing MP models is that it is weak in the sense of generalizing across the tasks. So an apparent limitation is that what people are typically doing as a benchmark for the neural process model is to train their neural process model on Gaussian process generated data, and then to see whether their model is able to recover the Oracle Gaussian process prediction. But in order to do that, you have to fix the dimension of the Gaussian process data. So if you have trained your MP model with 1D Gaussian process regression data, then it wouldn't be, it would not even possible to compute predictions for, say, 2D regression data or 3D regression. So I think this is often underlooked limitations of the existing pre-trained models, especially. In language model, we have like a fixed vocabulary size. So in some sense, the dimension of each token is fixed. So you don't really have to worry about generalizing across different dimensions of the tokens. But if you want to, like, build some kind of generative model for arbitrary continuous data, then you are, of course, you can somehow tokenize your continuous stream of data and then just use fixed dimensional tokenized input to your continuous generative model. But I believe more interesting solution would be learning a model that can, like, work in a dimension agnostic way. So it can encode any data, data of any input dimension or output dimension. So we came up with this architecture called dimension agnostic neural processes. So the idea is quite simple. So what you do is you first encode your input data, X and Y pair, in a dimension agnostic way. So in order to do that, you need to, like, apply the transformer like layer in the feature axis, and then you aggregate those encoded dimension agnostic representation using, like, the typical transformer-like architecture to do the prediction. So the architecture itself is not really, like, new, but we managed to show that this works quite well. So here in the top row, I show the figures of our models applied to various Bayesian optimization problems. So the DAMP, the red one, is ours, and all the other models are dimension-specific models. So for instance, if you want to apply the existing model to 1D regression problem, 1D BO problem, you have to train it with 1D data. And in order to do the 3D data, you have to train it with 3D data. But here, our model is just a single model for all experiments. So a single model trained with, I believe it was using only 2D and 3D data, managed to, like, solve the Bayesian optimization problem for 1D, 2D, 3D, or even hyperparameter optimization problem for CNN problem. And what we also found is that once trained, our model can extrapolate over the dimensions that has not been seen during the training. So we confirmed that, for instance, in case of regression, our model trained using 2D and 3D data can generalize to 7-dimensional regression data, so, which is quite remarkable, in my opinion. And the bottom row is an interesting experiment we have done in our paper. So where we originally train image completion model, which means that you have to take 2D coordinate and you have to predict the pixel intensity corresponding to the 2D coordinate. But here, we train our model using those 2D data and then apply it to video completion. So we create a video out of these images and see whether it readily generalizes to this 3D coordinate prediction, and it works well. Even like comparable to the model just trained from scratch with 3D data. So it shows some premises on our objective of like learning demand agnostic way of doing prediction. And I think I must have a slide summarizing this one, but so for some reason I'm missing the slide summarizing this work, but what I want to say here is that so I believe that this direction, learning a general stochastic process model in a data-driven way, I believe this to be a stepping stone of my long-term research goal of learning a foundation model to do statistical inference. So rather than choosing a problem-specific prior distribution for each problem of interest, and then doing like problem-specific posterior approximation scheme, what do I want to do is that we learn like very generic purpose prior distribution, and then use it as a good initialization for any problem that you want to apply to. Like just like you train a large language model and do various downstream tasks. So in some sense, I want to do it I want to build a large language model, but for like arbitrary continuous real numbers, so that you can use it to solve any Bayesian inference problems for like any downstream tasks. So under that direction, under that long-term goal, I believe this learning neural processes in a dimension agnostic way is an important stepping stone. Okay. Before moving on to the second part about the inference scheme, do you have any question up to the content so far?
What's the intuition that you can actually do this from smaller dimension to higher dimension?
So we believe that the model is capturing the inter-data relationship rather than trying to just manipulate the instance-wise information. So for instance, think about the linear regression problem. So the form of the least square estimator. Of course, it involves like doing matrix multiplication, but if you have a look at the form of the equation, you see the structure, right? So it computes some cross covariances between correlations between the data points, and then trying to interpolate the training data using that correlation. So we believe that this model can learn not to just capture the dimension-specific covariance, but to capture those interrelationships between the data points or structures required to solve.
Saying it works because it's non-parametric.
Maybe, yeah. Although this model is parametric model using neural networks.
All right, sorry.
Okay, then let me move on to the second part. The second work is about learning to do stochastic gradient MCMC in more efficient way. So this was published in recent ICML. So the basic idea is to learn a stochastic process. So let me continue. So yeah, our goal is to learn some terms required to define a stochastic gradient MCMC algorithm, rather than like hand specify them, learning them from data. So, and a good thing about our approach is that ours can generalize across different neural net architectures or datasets. So the stochastic gradient MCMC algorithm, it has been proven in 2015 paper that any SGMC algorithms converging to a target posterior distribution should be written in this form. So we have this stochastic differential equation, and depending on the choice of the terms involved in this recipe, you get like different special cases. So there are design choices to be made. For instance, you have to choose the form of the kinetic energy term here, and you have to choose these two matrices. One is called the diffusion matrix, which is a positive semi-definite matrix, and the Kerr matrix, which is the skew symmetric matrix. So for instance, if you choose these, choose the kinetic energy to be a simple Gaussian, which is the standard choice for the most of the algorithms, and then you choose these two specific diffusion and Kerr matrices, you recover the stochastic gradient agency, which is the most popular algorithm, SG-MCMC algorithm for Bayesian neural net nowadays. So there was a previous work which was trying to, rather than hand specify these design choices, learn them from data. So it was 2018 paper, so where they keep the kinetic energy to be the simplest possible Gaussian kinetic energy, and then parameterize the diffusion and Kerr matrices with neural networks. So they, but theirs was a pioneering work, but theirs were quite limited, both in terms of generalization and scalability. So they didn't showcase whether their method could generalize across different neural net architectures, or their method was indeed available. It was possible to apply their method to large-scale BNN experiments. And especially the training procedure is quite unstable, so they use like quite complicated objective function, and as a result, the learning estimating the gradient to update those parameters. So theirs was quite inefficient in estimating the parameters. So in our work, what is called the learning to explore, we made like different choices. So first, rather than trying to learn the diffusion and Kerr matrices, we learn to parameterize, we parameterize the kinetic energy. So rather than making it a simple Gaussian, we want to learn it like as flexible as possible by using neural networks. And then we, of course, demonstrated our meta-learned SGMC algorithm indeed generalized across various architectures and datasets, so that once trained, you can use it for like various tests that you want to apply. And we, as a technical contribution, we came up with a better meta-gradient estimator and so on. Yeah. So let me be specific about how we parameterize our sampling algorithm. So we proposed two parameterizations. So each of them has their own limitations, but in terms of empirical performance, they do like they perform quite well. Both of them have shown similar performances on various benchmarks. So the first one is in order to do the SG-MCMC update, you have to compute the gradients of the kinetic energy with respect to the parameter theta and the momentum r. So here, rather than explicitly specifying the kinetic energy function, we just parameterize the gradients of the kinetic energy with respect to the parameter and the momentum using neural networks. So if we do this, then we end up with getting like a simple update equation for which we have to learn the parameters. But the caveat of this simple approach is that given these free-form networks alpha and beta, which are approximating the gradients of the kinetic energy, there's no guarantee that the corresponding tree satisfying this condition would exist. So this would be a limitation of the first approach, but it is like most convenient to work with, especially for meta learning perspective. The second parameterization we have tried was to keep the Gaussian kinetic energy form, but instead of just letting it to be the simplest possible Gaussian without any information, we choose to be the Gaussian centered at specific position depending on the current position theta. So if we do this, the corresponding update would be like in equation 13. So now by design, this parameterization guarantees the well-defined kinetic energy term, but the problem here, a downside of this parameterization is that while doing the computation, you have to compute the gradient of this neural net with respect to the parameter data, which can be quite costly, especially for large models. So we have tested these two approaches and they performed similarly. So I will just show you the result. So, and of course, for the meta objective, we came up with a better and easier to use meta objective compared to the previous one. And for the gradient estimation, we are adapting the evolution strategy, which is more amenable to long horizon calculation and parallelization. So using our recipes, what we showed is that, so here, the fact we train our meta model only on fashion MNIST data, which is black and white data, and we just using like a limited set of neural net architectures. So we train, so the way we train is that using the meta parameters we use to define our SG-MCMC algorithm, we do some unrolling, optimize the meta objective as well, using like multiple tasks. And then after the training, we deploy the learned MCMC sampler for various tasks, not necessarily for the one we have seen during the training. So here, the only tasks we have seen during the training is the fashion MNIST. But you see that like ours trained only with black and white fashion MNIST data already generalized well to CFAR 10, 100, or even tiny ImageNet data. And for the CFAR 10 and CFAR 100, we have an oracle, the samples collected from the HMC. So there was a paper in 2000, I believe it was 20, by the researchers from Google, where they used like tons of machines to learn exact Hamiltonian Monte-Carlo law on these problems, and then they provide the checkpoints. So you can consider those HMC solutions as an oracle, and you see that ours, the meta-learned sampler from our recipe is quite comparable to HMC for this type of data and works a lot better than the previous one or hand-specified SG-MCMC algorithms. And we analyzed why ours is better in terms of predictive accuracy or uncertainty quantification. What we have found is that the sampler learned from our algorithm tries to explore more, especially discovering multimodal structures of the posterior distributions. So you can see from here, we visualize the loss surfaces of the samples found by various samplers. And as you can see, especially from the second figure, so different samples collected by our sampler, this one, is more, has larger barrier between the samples, which means that they are placed in multiple modes in the loss surface, especially compared to the SG-MCMC, which was like the standard choice for BNNs. You can see that the samples collected from SG-MCMC, the C-SG-MCMC, are all, they all reside in the same Bayesian attraction. But ours, using the same computational budget, was able to discover the samples that are much more apart from each other in the loss surface. And you can actually quantify this barrier where we just place multiple samples and compute the loss barriers along the line. And you see that the chain discovered by our sampler exhibit higher loss barriers between the samples, which means that our sampler is indeed discovering multiple modes that are apart from each other compared to the previous one. And we compute like effective sample size or the other metrics to assess the mixing of the samplers. And in our paper, we show that ours indeed like improve a lot compared to the baselines. Like either it is hand specified or meta learned using the previous modes. And this is not really interpretable figure, but I'd like to show that here, for instance, in this leftmost figure, what this beta network is doing is that even when you don't have the gradient to move the current position, you still get non-zero contribution from this beta network. So it encourages exploration in a different way from the previous rules.
Sorry, could you explain the X and Y?
Okay.
It's not very clear. So,
yeah. So for instance, this figure, the beta network is the term being added to the update at the final equation. So even when the gradient, the gradient of the energy of the current model is relatively low in this regime, you still get like non-trivial contribution from the beta network, which means that even when you are in the local optimum, the model still tries to explore to other position, while the other sampler, especially the hand design samplers, don't really have this kind of behavior, so that you have to artificially control the learning rate, step sizes. But ours just do that automatically. And the third part is about accelerating the prediction. So this one is about computing the Bayesian model averaging. So say you have collected multiple samples from your posterior, either using MCMC or variational inference or whatever. So now you have to compute the predictions by doing Bayesian model averaging. So of course you cannot compute the integral exactly. So what we typically do is, of course, in case of like linearized model, you can do the probit approximation. But if that is not the case, what you usually do would be the Monte Carlo approximation. But the problem here is that, as I mentioned earlier, the cost of computing each h, so here should be subscript k, j here. So to compute each h computed for the theta j, you have to go through the forward pass through the deep neural network. And the cost of doing this, of course, is not negligible anymore, especially for large models. So how can we reduce this cost of doing Bayesian model averaging? So there may be like three possible ways. One would be the model merging, like the stochastic weight averaging whenever it is possible. Or other two approaches that I'd like to introduce today would be the ensemble distillation and bridge construction. So ensemble distillation is like you collect this Bayesian model averaged teacher, compute the Bayesian model averaged teacher, and distill it into single model. So, and hoping for the pseudo models to capture as many aspect of teacher model as possible. And the third approach is a rather unfamiliar approach, because our research group is the only ones who are doing this in some sense. So it is like, rather than trying to compute all of these predictions for each parameter, what you do is you just compute the prediction for the one of the models, and then you construct a bridge between the predictions from those one model to the average model. And we show that we can do this quite efficiently and accurately. So I will show you what do I mean by this bridge construction more in detail later. So in terms of ensemble distillation, so it is like a typical knowledge distillation work. As I explained earlier, you get a teacher model, you set a teacher model as an averaged model, and you set up a student model be like a single neural network. But if you just do a naive knowledge distillation here, you end up in getting like really not good model. And throughout these two papers, we propose two solutions to like combat with that suboptimality. So what our two ideas is, so basic story is that you do the knowledge distillation. So in case of classification problem, you compute the softmax predictions from the teacher model, which is the Bayesian model averaged model, and you want to minimize the cross entropy between your student model prediction and the teacher model prediction. But this is, of course, a naive way of doing this. This is suboptimal for two regions. We argue that for two regions, this naive distillation is not really good. The first one is, of course, the student model has limited capacity, so this is just a fundamental limitation of knowledge distillation. And more important limitation, especially in terms of ensemble distillation, is that if you just distill the averaged prediction into a single model, you somehow just summarize all these individual predictions into a single one. So in other words, you are missing some diversities in between the predictions using those multiple models. But we argue that those diversities are somehow crucial in prediction, especially in Bayesian model averaging. The power of this model averaging, in some sense, partly comes from the diversities between the predictions from multiple models. So there should be a better way of delivering this knowledge, especially these diversities among these teacher models into the pseudo model. So for improving the capacity of the pseudo model, we propose to what we call as branch and merge type of distillation. So the basic idea is can be summarized using this figure. So what you do is, given a single model, so you have these multiple teacher models. Say you have 4 models in this figure. So you want to distill the average of these 4 models into a single pseudo network. And what you do is, rather than just aggregate these 4 models into a single one and directly distill those aggregated models into a single pseudo model, what we do is we create 4 subnetworks inside this single pseudo network. The way we do this is is similar to the low-length type of approach. So more specifically, what we do here is that for each weight parameter, we parameterize the weight parameter as a backbone parameter phi perturbed by low-dimensional, low-length factors, as we do in the LoRa. So, and then the multiple subnetworks are created by just varying these low-length factors and sharing the backbone parameters. By doing this, we can create subnetworks out of a single model without increasing too many parameters. So then, once we have created these subnetworks, then rather than just trying to distill aggregated teacher directly, so what we do is do the distillation in one-to-one fashion. So we match each teacher to each subnetwork. Then we distill individually. And then after that, once we have learned these students, we post-aggregate these subnetworks into a single one.
Is the perturbation somehow shared between them? Between the teacher and the student? Is it the same perturbation?
No. Teacher is without any perturbations.
Okay.
Yeah. So only the subnetworks are.
I see.
Yeah.
Sorry, we have maybe 5-6 minutes left.
Okay.
So
I will be key. So yeah. So then the way we merge the subnetworks after the training is simple. So you can just take the weight averaging of these rank-on factors, and then you will end up getting a nice single model that is much more competent than the single model trained in another way. So another important message in this knowledge distillation is that in order to get the maximum diversities out of the teacher models, what you have to do is you have to apply a well-designed perturbations to the training data. So for instance, in this simple example, you have 3 models. If you train on the training data, they will all agree on the predictions, right? Because your model are likely to be overfitted to the training data, so they will all achieve 0 training error. So if you train just using the same training data, you won't get really out of much diversities from these teacher models. But if you apply the well-designed perturbations to the input that are nearby, then now the teachers start to disagree with each other. So what we have found is that rather than trying to distill using this original training data, if you train with this perturbed data, you will get much better diversities in the pseudo models. So we have proposed 2 types of perturbations that can be computed efficiently. And what we have shown, especially, is that if we combine the ingredients that we are proposing, for instance, in CFAR 100 classification, using a single model, you can do almost as good as 3.167 models. So this is quite a nice message to summarize this work. And finally, what do I mean by the bridge construction is that, so here, you have 3 models, and you want to compute the average of these 3 models. So originally you have to follow the right path. So you put the input data into each of these three networks, compute the predictions, and then take an average. So what we propose to do is to take the left path, where you only compute the predictions from the single model, and using this single model prediction, you gradually change the prediction from the single model into the averaged prediction using the diffusion bridge. So this is like a distribution matching problem. How should we match the distributions, predictive distributions computed from the first model, single model, and the predictions computed from the averaged model? So we showed that this can indeed be done quite efficiently by only attaching a lightweight network that transport the predictions from the single model into the predictions from the average model. You can indeed like improve the accuracy. Accuracy per inference cost a lot. So this graph shows the result. So the diagonal line would be the ideal full Bayesian model averaging, and if you follow our approach, for instance, so the orange one is the other bridge construction work that we have done in previous year. So it is using inferior version of this work. So if we do this, we show that ours can indeed have a better trade-off between the inference cost and the accuracy. So the main message was that you can indeed transform the predictions from the single model, which is in the leftmost bars, to the ensemble prediction, the rightmost bars. So you see the gradual transition from the source, the single model prediction, to the target model prediction using these diffusion steps. So to wrap up the talk, so I believe the famous article by Rich Sutton, a bitter lesson, we have more success when we reduce our human intuition and try to exploit more data, exploit more scale. I believe this message also applies to Bayesian deep learning in some sense, we build priors rather than based on our intuition, try to build it from data. But because even for this scenario, I still believe that Bayesian principle becomes even more important, especially in order to understand what is going on for these priors or inference algorithms learned in data-driven way. And also, especially from the perspective that I got from the work in neural processes, I believe we are increasingly likely to work with a single generalist model that is continually learning over multiple tasks, rather than just trying to learn specialist models for individual tasks. So in this case, I believe this Bayesian principle is more important, especially I believe Bayesian is all about continual adaptation to real-world environments. So yeah, in that sense, I still believe there is a significant room for Bayesian deep learning, Bayesian principle, even in the age of foundation models or generative AI. But to achieve that, we need a rethinking of the algorithms that we have been using so far. So yeah, that is our message. That is my message. So thank you for your attention, and I'd be happy to take any questions.
Thank you. So it is almost 12:30, but because we had an interruption in between, so let's have 5 minutes of discussion. People have questions?
Cool, thanks for the talk. I have a lot of questions, but I'll keep it short to one for now. So for this sampling thing where you showed the different modes that you sample from and the kind of loss landscape in between, I was wondering, because you were also citing this paper by Andrew and Pavel and so on about the HMC stuff, right? And they make the argument, I guess, that they expect the different modes of the posterior to have some low loss connections, and so in their paper they show that their HMC sampler actually has low loss between modes, and so it finds these what they call low loss tunnels or something.
So I guess they make the argument that having low loss between the modes is a good thing, and from what I understood, you were saying like you have a high loss in between, and that's a good thing because you find different modes. So it seems like the opposite argument. Do you have a kind of,
yeah. So actually, if you have a look at the short-term like thinning intervals, they do reside in the low loss term because in order to make HMC samples to be accepted by metropolis testing corrections, you need to choose like quite small step size. So each steps of the samplers are moving quite slowly. So in the short term, as you said, they are moving across the low loss kernel, and it is indeed good in terms of the acceptance probability. Actually, if you try to do the metropolis testing expressions for like typical SG-MCMC algorithms with the learning rate that we typically use, like more than 99% of the samples will be rejected, which means that they are moving quite quickly. So it is quite bad, right? So, but what we are trying to show here is that our sampler is discovering the long-term transitions that would have been discovered by like very small step size HMC using like much large number of steps. So that is what we were trying to show here. Yeah.
This is a very important point. It's learning to explore is directly connected to this finding places where solutions that are good enough but then are different.
Yeah.
Right? And I think in deep learning it's trivialized to say they should be always connected. But if you have balanced data sets, it seems like that would be okay.
Yeah.
Right? But barriers are good if there's entirely two different ways to solve the same problem.
Yes.
There should be a huge barrier between them. It just makes sense. So all of this lottery ticket hypothesis of linear mode connectivity, I think it's narrow because we are looking into very specific problems with a lot of data sets. If you talk to people with RL, I think they'll agree that if there's a maze and there's a completely entirely different way to get to that in two different ways, they should be far away from each other if you do the modeling right. So I think we need to think a little bit more than, but it's a very good question actually. Sorry, I'm not the speaker, why am I answering? Any more questions?
Hi, thanks for the talk. So, are there any cases like where exploring can worsen the performance of the sampler? For example, I'm thinking like high dimension.
A particular case we have found the exploring is not really helpful would be the transfer learning scenario. So where you start from a well-informed initial position, like you have trained your model using like larger data, and you initialize your model with the pre-trained model. Then, in case of having a pre-trained solution, if you try to explore too much away from that pre-trained solution, we found empirically that that exploration is not necessarily leads to the gain. So I believe if you have a strong prior belief about your solution, then exploring is not as much needed as it is like from scratch scenarios.
I have a general question. We always compare Bayesian and Bayesian approaches. Is there a comparison between classical approaches where you compare, say, Bayesian transfer setting and bias?
Oh yeah, so I believe we do have the table, for instance, in transfer learning, I'm not sure.
So this small table, very small table.
Yeah, very small table. Yeah. There's no point estimate comparison in this table, unfortunately, but we do compare ours to the point estimate transfer learning in this scenario, and Bayesian is better, both in terms of accuracy and especially in negligible value, which means that they are much better in conservative application.
What's the stereotype method for classical?
Like the standard transfer learning here in this case, and also like in the method like L2SP, so this is like the one I presented here.
Do you mean like non-Bayesian?
Yeah.
Maybe it's non-Bayesian.
So you apply this regularizer in, you employ this prior centered at the pre-trained parameter, and then you just do the map estimation using this as a regularizer.
But this is like the assumption, right? You assume that some performance is
Yes. No.
This like we assume that this is sort of the assumption. The distribution will get by.
Maybe you're saying this is still Bayesian.
I mean, you mean even if we are doing map estimation, this is still Bayesian, right?
Yeah, because you're assuming the sigma square. It looks like Bayesian, there's a Gaussian.
Okay, then you can probably refer to this one. You just initialize the model with data not, and you just throw it away.
And you fine tune it.
Yeah. And even like doing map estimation using data not in this way is a lot better than just initializing and fine tuning, not doing any sort of regularization. Yeah, in the paper.
Maybe we should just written that paper.
Okay.
You know? That's where the community is. You know, anything heavy they cannot take. So just that sigma square. Okay, what's there? Okay, maybe in the interest of time, let's close the session. So let's thank the speaker.
Last talk of the day, which is Alex. Alex is a PhD student in his final year at ETH Zurich and the Max Planck Institute for Intelligent Systems, and currently is also a researcher at Google. And yeah, he's going to talk about advances in Bayesian model selection for deep learning. With that, just take it away.
Okay, thank you, Vincent, for the nice introduction. I'll add a bit to the bio, sort of for the sake of explaining where the topic comes from. 5 years ago, I was an intern here in Emtiyaz team for a year, and that's where I got in contact first with marginal likelihood or Bayesian model selection for neural networks, and sort of that also is something that I worked a lot on during my PhD. So I'm going to talk about advances. So I think two years ago, I also gave a talk here at RIKEN ARP, which was without the advances, so just Bayesian model selection and deep learning. And today I'm going to talk about what sort of happened since then. And in particular, I want to talk about two things. The first thing that will be sort of a bit of the background, how this works, when this works, and what are interesting applications for Bayesian model selection and deep learning. And in the second part, I will actually talk about duality. I have the feeling actually for the first time of the day, we will see some duality, some equations. And yeah, it's I think kind of interesting and fitting for the workshop. It shows how duality can help you sort of to get faster estimators of the marginal likelihood that is relevant for Bayesian model selection. All right, so I don't have to introduce notation or anything that much because luckily Vincent used the same one this morning. So we have some kind of data set, can be supervised or unsupervised, of n data points. So n is an important character here, d for the data set, theta for the parameters or neural network weights, and m for the model. So this is kind of what we put the hyperparameters into. This can be architecture, this can be regularization. It really depends on the application in the end, what this calligraphic m is. And the neural network function is fx and parameterized by theta. All right, so I don't need to, okay, maybe I should convince some why we should do any Bayesian learning at all, right? To sort of contrast it a bit with normal deep learning, what we do in conventional or normal deep learning is we have something that usually looks like a likelihood, right? So P of the probability of data given the parameters theta, and then we have a prior that sort of specifies what kind of parameters are a priori likely. And so then we sort of maximize this, or if we want to cast it as a loss, we minimize it. What we end up with is sort of some small, some point estimate in this case, right? So, okay, my cursor doesn't work, but I'll just, you can see the dot there, right?
It works, you can see it.
Yeah, no, it's, I think, really? Oh, it's kind of, it doesn't go where I go actually. So, yeah, so I'm not going to use it. I'm just going to try to move it away actually. Okay. So yeah, so in conventional deep learning, we just maximize this, and so if we have a point estimate, and we compute predictions with that, right? And so the difference then to Bayesian deep learning is that we need to get this normalization constant. So we want to divide this joint probability by the normalization constant, so by integrating out the parameters, so theta in this case. In this diagram I have in the bottom, this is fairly simple, right? We can, I mean, actually it's not that simple to begin with, because it could be multimodal and whatnot, right? But in this view, it's relatively simple because we can sort of visualize it. But in reality, if we have a neural network, we have theta that is a million, billion dimensional, whatever these days, right? So we can't really compute this normalization constant. But let's just assume we could. Then what could we do with it? Why would we even care, right? Why would we opt to do the right-hand side when we can just go with the point estimate? Does it give us any benefits? And I'll briefly talk about two benefits that I think are sort of the most common. So first is probably the most common. So the first one is uncertainty quantification, afterwards another one. So posterior predictive is what we've seen today, I think, a lot already. So what we can get is this model uncertainty or epistemic uncertainty as well. And you can see what basically happens is we integrate against the posterior here, and which I visualize at the bottom again, and we then get in the predictive these epistemic uncertainties, right? So depending on the posterior, you have also more uncertainty in the predictive. And I think what's also worth mentioning maybe is in comparison to maybe the CP confidence or like the bounds that you get, we have a decomposed uncertainty in many cases, right? So we have something that's the aleatoric uncertainty. So for individual, because we have a likelihood, right? So for individual targets, how noisy are those, for example, because of measurement errors? And then we have separate from that the epistemic uncertainty. So how uncertain is the model about its predictions? And these can sort of vary in different ways. Okay, so this is just sort of as a background, right? So I'm not going to talk about this today. There's also a lot of interesting work on that, right? And I also work on this, but today what I want to focus on is another advantage, I think, which is the idea of Bayesian model selection. And there we really use this denominator in the posterior. So we use this integration, which I just showed in the beginning as well. So we need to compute this integral here. So we need to integrate out theta, which is extremely hard, of course. But so assuming we could do this, then you could say we can balance model complexity and data fit, right? And the reason for this is, and I'll just sort of glance over this a bit, if you have this marginal likelihood, it's called, P of data given model, then a model that is extremely complex that can generate a lot of data sets. So it can only assign very low probability because it has to normalize to 1 over all the data sets. And a model that is too simple, like a linear one, can only generate one particular data set and has very high density on that. And you want to have a model that's sort of just right, so where the complexity is adjusted to the data set. And that's what you get sort of in the middle between the two. And so I've visualized here also this example. So a too simple one, in this case, is over-regularizing. A too complex one is a too big neural network that you overfit. And just right, I guess we would all agree, looks, in this case, the best. I also put here an asterisk for the reason that you can also make this go wrong, right? If the prior is not well chosen, if your probabilistic model kind of doesn't allow for this complexity and data fit, then the whole procedure doesn't work. So there are examples when you want to optimize too many hyperparameters, then you will just overfit. Then in the end, it's just like it doesn't really make much sense. So you have to choose a set of hyperparameters that allow you to actually control the complexity. And
it's not just the prior; it's anything.
It's anything, yeah. For example, the prior, but I particularly wrote also here, right? It can be also the architecture. It can be anything as long as you don't make it, let's say, too easy for these hyperparameters to fit the data themselves, right? If you do things that are more exotic, so let's say you put all the neural network weights into your hyperparameters, you will easily overfit, and then you get something like deep kernel learning or last layer variational inference. These things, then the marginalization doesn't work anymore, right? Because you marginalize over two variables in the end.
That is true for anything.
Yeah.
Some things for it doesn't work. So.
It's for anything, exactly. There's always counterexamples, right? I think I just want to take this up front because there are cases where this won't work. You can find examples for this, of course, yeah. But yeah.
It's not magic.
Yeah, it's not magic, exactly. All right. So, yeah, is anybody absolutely not convinced that we can do this or should do this? Okay.
I'm actually a bit convinced, but I have just a short question.
Yes.
Is there a actual proof of this Occam's razor scheme outside of GPs and everything Gaussian?
is there actually a proof for GPs? So yeah, I wouldn't know if there's any proof, to be honest. Like for me, so I rather rely on empirical proof in this case. I think we, especially at scale, we have to try the things out and see if they empirically can work or not, and sort of do enough exhaustive evaluation for it, I would say. Yeah, so I don't think so. But I'm pretty sure you can sort of, as Andrew said, you can always make it go wrong, and I think this is relatively easy in this particular case, right? You can choose the M such that it will easily overfit.
I think some Bayesians very blindly believe it, which doesn't make sense.
But even in GPs, it can go wrong, right?
Yeah, exactly.
It can always go wrong.
Can always go wrong.
If it doesn't, it's magic.
And magic doesn't exist, right?
Yes.
Exactly. Yeah, that's a good point. But this is quite close to magic. At least when I first learned about this, I was quite surprised how well this works in GPs, and I wanted to really get this to work for neural networks. So that's why I hear about this now. And so one approximation that I've been working on a lot, and that for the reason that it actually allows us to do these kind of procedures, is the Laplace approximation, and that's why I'm going to quickly introduce it. This choice is actually because I tried out different approximations and they didn't really work for Bayesian model selection for neural networks, and somehow for Laplace approximations they right away worked relatively well. There's not much that one has to do to get it to work, and if you're not familiar with them, it's really the simplest possible posterior approximation I think you can make. We take the posterior, we find the mode, so we do the normal neural network training procedure, and then at the mode we estimate the curvature. And this will give us then a Gaussian centered at the mode with the covariance or the precision dependent on the Hessian curvature. So really as simple as that, like literally the images show you exactly how you would do this. And in equations, what you would do is for the posterior approximation, you have the negative Hessian of the log joint at the mode, and you have to invert that for the covariance. And for the predictive, you integrate it against that. And now the interesting part, the log marginal likelihood, so the normalization constant, looks super simple as well. You basically just have this first term here, so the log joint. So that's basically just the loss that you optimize anyway. And then the second term basically penalizes your complexity, right? So you have this negative log determinant, and so the larger the determinant will be, the more penalty you will incur for your model. And so this is particularly the equation that we will sort of deal with. The first problem that you will have, that one probably didn't have before, at least before 2010, is that the Hessian is not tractable, right? So we have, let's just start with 1 million parameters, right? Like, that's already a small neural network by today's standards. And we want to compute the Hessian and invert that as well. So you couldn't really do that if you don't do any approximations here. And so the first step is to do sort of approximations to the Hessian that are sort of more structured and that are more computable. And I think sort of the most successful are probably block diagonal approximations like KFAC, so Kronecker factored approximate curvature. Or if you want to go all the way, you can do a diagonal as well, right? And low rank is a bit more exotic, but what I want to show here is there's sort of a progression, right? You can go from the full one and you can approximate more and you go all the way to the diagonal, but we don't go to the last layer. We always model all the weights in this case. And what I quickly want to mention is you can use KFAC for LLMs as well, right? So this is being done, this is possible, so they scale to any model that you really want. The second change to the algorithm of sort of empirical Bayes or Bayesian model selection that we made was actually in 2021 with MT was to optimize the hyperparameters and the neural network weights simultaneously. So normally when you have a Laplace approximation, you have to get the mode, right? But the question was, like, what happens if we're not at the mode? Can we still do something? Can we still use the marginal likelihood approximation as is to optimize hyperparameters? And empirically, it turns out that this is actually still possible. And it also turns out, as Juho Lee from Cambridge found out, that it empirically somehow works even better than sort of correcting for this approximation. So if you train to the convergence, you do the update, and you do this for a very long time, this works worse than doing this online model selection, which is kind of interesting actually. And it also works worse to use a correction term, which you can actually compute, which we tried back then as well. It was just like more expensive to compute, but this simple algorithm actually sort of seems to work for neural networks already. And the cool thing is now that I haven't really made any assumptions, particularly about M, right? It can be a large set of hyperparameters that are differentiable, right? So things that we do have like thousands, even millions of hyperparameters, and they can be just differentiated. And because gradient-based optimization is just very effective in the end, right? It's like what deep learning is based on is SGD, right? So we want to do also something like that for the hyperparameters. So for example, what Vincent has shown this morning, this sparsity work, there the set of M of hyperparameters is as big as the neural network weights. So this is a huge set of parameters or hyperparameters. And the second thing is that's probably debatable to what extent that can really work, but you can also do discrete model selection. So here again, caveat, there's I think some theory why this would not actually work in some cases. And also in practice, we see that if you compare across two broad families of models, this will not work anymore. But if you stay within sort of one class of models, this does work. Okay, so I'll give you briefly one example, which is about optimizing weight decay or prior precision. And it's exactly the same example that you've seen in the beginning. So what we do here is we train this neural network on the simple data set for regression in a single training pass, and you can see 3 different curves that optimize the prior precision parameter during training. So you start maybe from a high regularization, or a low one in blue, or medium one in red. And what I want to highlight is they all end up in the same optimum, which you would also find if you did cross-validation in this case, but just with one training run. So this is kind of cool that this kind of works for this. And if you did cross-validation, right, you have to train more than once, and it still costs way more as well, because training with the marginal likelihood is probably 2x slower at worst, something like this, usually even faster. So now I want to briefly, as I said before, mention some advanced applications maybe that we've worked on in the past years that I thought were quite interesting, that you can sort of solve these from one common empirical base principle, let's call it. So you define some hyperparameter set that you want to optimize with gradients, and then you do this during training, so you don't need to do anything on top of that. The first thing is about invariances and equivariances. So invariances, I'll just briefly explain, are sort of in your data set. For example, let's assume you have a data set of dogs and cats, which is like the classical example, right? It doesn't really matter for a dog or cat if it's completely rotated. I mean, it's a bad image if the dog is on the other side, but it doesn't actually matter for the label how much it's rotated, right? So you want to be invariant to that. This is something that we can encode if we know it by data augmentation. But let's assume that we don't actually know about our data what this invariance should look like. Then we can parameterize a network. So we have this fx data and eta controls the invariance. We can do this by some generating function such that eta controls our amount of invariance. So how much rotation we want to do, how much other transformations we want to do on images or any kind of data. And as you can see in the bottom, you can just use this as an objective and you learn the correct invariance that you put into the data in this case very early during training already. And yeah, you don't need any additional prior knowledge about it. And I think the also interesting thing is here, if you were a full Bayesian, so I'm basically here being an empirical Bayesian, right? If you were a full Bayesian, you would have to integrate this loss curve as well, because this is then the distribution over eta parameters. And I think it's interesting here to see that basically 90 degrees rotation is sort of optimal, but higher is also fine. So there's also some posterior mass on higher invariances, which in this case actually makes sense. This is, I think, on MNIST where we rotated the digits by 90 degrees, and the model can actually distinguish 6s and 9s even if they're fully rotated. So that's why you can do full rotation. It doesn't even make a difference in this case. The second thing is some biomedical application that I thought was kind of interesting. So there you have heteroscedastic noise terms. So that means every protein and RNA marker has a different sensor measurement noise. And you kind of want to integrate two data sets. You have RNA measurement for each patient, you have a protein measurement for each patient. And if you want to learn representations from that, you need to find out how relevant are the proteins and how relevant are the RNA measurements, right? And putting those together is something that you can do very well with Bayesian model selection, because you will regularize the modality respectively by how important it is for certain things. And you will also be able to learn how much observation noise you have for different data sets, for different modalities as well. And in the end, I don't want to go into detail on this, but in the end, what you get is this RFR model, which can combine sort of the performance of the unimodal model. So it will always get the best of both worlds, in most cases at least. And if you do just like maximum likelihood or map training, this was not the case. So like the Plier and FA baselines don't have this property, which is kind of nice. Then one discrete model selection that's what we did. I mean, it's mixed discrete and continuous model selection. There's this problem of probing language models, of figuring out what kind of knowledge or what kind of information is in the representations that language models learn. And in this case, what you need to sort of consider is the model that gives you the representation, as well as the probe that figures out what linguistic property is encoded in that representation. And it is sort of interesting that we found that different representations require different complexity in terms of the probe, right? For example, in the simple task, Boole, Q, and RTE, you just need a linear model, and you can sort of already extract the linguistic information. But if you have more complex tasks like this one here, you need two-layer MLP to get sort of the information out of it. And sort of before, people said, or sort of tried different things where they would only use a linear model all the time and say if it's not encoded linearly, then it's not encoded. But this doesn't make sense if you come from the perspective of sort of getting the information out of the representation. Okay, so there are also lots of other applications. I mean, Vincent also talked about two more, like the sparsity, the neural additive model. There's some other stuff as well. But I hope I sort of somehow convinced you a bit that there are some interesting methods, interesting problems you can solve with this differentiable or even sometimes discrete Bayesian model selection. And now, maybe we can sort of, if there's anything we can discuss it maybe now before I go to the theory part, and then we can talk about the duality aspect that comes into play as well to get faster estimates. So maybe here first some questions. Yes? Can you speak up a bit? It depends. So that depends on how you set the prior, but in this case, we would do either row or column-wise sparsity, or actually every individual weight would be regularized. That would be the most number of hyperparameter setting, right? So for every weight, you have a Gaussian, and you control its variance of precision, and you optimize that. That means that some weights will be completely regularized and some will be not regularized. This gives you sparsity in the end, or like something that's numerical sparsity. It's not exactly sparse, but it's numerical sparse. So I cannot hear. Yes, but I mean, in this case, so as I mentioned, I mean, it's not exactly sparse, but it's numerically sparse. So it will go to 10 to the -6 or values of like that. And then these you can just set to 0 in the end, and in the worst case, fine tune a bit. But usually you don't need that. You can literally set that to 0. Okay, so then let's do some duality, some math. Finally. Okay. So yeah, okay. Please go ahead.
Do you explain like how to theory on that, right?
Yes. Yeah.
Did you look into like have people seen any connections to the complexity measures that we do in other?
Yeah, definitely. I think I mean there are like connections to pack Bayes. That's one thing that sort of we also are working on and trying to figure out what is there. There's a lot of research on, I guess, Hessian-based complexity metrics, where people add a trace, or they compute the log determinant, which I'm also doing, right? I think these are all like perfectly valid and maybe also work together very nicely. The difference is often that they don't know which factors to put in front of the things. And so this, if you just put like a trace of some Hessian and it's the average Hessian, it's a different thing, right? So I think the important bit in the end to get things to work is to sort of have the model written out and know what you divide by or multiply by. That's, I think, the main difference. So we can also use a lot of, I mean, this, for example, k-fact comes also in a way from second order optimization, and all the other methods that we're using come from complexity metrics as well.
Maybe I was just wondering, so also a question, but if you think of model selection, then basically it means you're making a choice on the family model, and then put a prior on the analysis of parameters or something, and then you choose basically on the parameters. Right? Have you ever looked into something more like what people in meta-learning or artificial intelligence, what they're also doing, like the actual structure of the model, whether the model itself is a good choice for that?
So I have in the paper that I did with MT in 2021, there are some figures where we take, for example, different resonance with different widths or depths, and then we compare them on data sets and see which one gives the highest marginal likelihood, and compare that to test accuracy as well. So that is also a form of the discrete model selection, right? So that also works, but that's in this case not differentiable. And if you want to do it differentiably, I also have some work which I think is the second one, but it's led and mostly done by Juho van der Hoedera. And there we do equivariances, and this is a type of architecture search, because how we parameterize is we have sort of always the choice between an equivariant layer and a non-equivariant layer. We can also control the amount of equivariance at the same time, and then you sort of choose between layer types. And what we can find is on image data you would go all the way equivariant until the last layer, and then you have a linear layer to classify, which will not be equivariant here. So yeah, it also does work for this. It's just relatively, like neural architecture search as well, hard to implement. It's not doesn't work that easily, I would say, because of all the differentiability aspects. Yeah, you satisfied with the question? Yeah, okay, good. Let's talk about it later. Exactly. All right. I can also show you later. Yeah.
Functional likelihood is like a prior prediction, right? Can we get some information from the prior prediction to posterior? Because what we really care is posterior.
And so, wait before you sit down.
From prior prediction about posterior.
I guess it depends on the prior. And so I think what you're suggesting is to probably compute the marginal likelihood by estimating this integral by sampling. Is that what you? Oh, sorry. Basically,
like this prior part is like if we care about the posterior prediction, the prior part will be replaced by the posterior, and this TD somehow.
It's the prior predictive, yeah.
Some real data.
Exactly. Yeah. No. So I think yes. I mean, in principle, it should be possible to do this, but this didn't seem to work. I think people have tried this. So basically, you can do like sampling-based estimators on this directly, but it doesn't converge, or it doesn't really give you anything. Unfortunately, it doesn't work in this case. So basically, the problem is that the priors are in the beginning at least too vague. So the Gaussian prior is too vague to get any meaningful prior predictive that would give you, for example, class labels for any images, right? So I think it's too hard a problem to go from the predictive and the prior level already. But yeah, I think it has been tried.
I think conformal prediction is bad.
It's the prior. Well, I'm not going to comment that. Okay, so well, that's good. I think so. Nobody overthrew me on sort of the usefulness of this, at least not yet. So that means you're at least a bit more.
Bayes-Duality, come on.
It's exactly now comes the Bayes-Duality part, which we're often waiting for, right? As the finale of the day. But first, as I mentioned, some theoretical preliminaries that we have to do. And there's the first thing is, I think it's a really nice theorem, or it's just called an inequality by Fisher, but with SCH. So it's not the Fisher from Fisher Information.
Not the eugenicist guy. Maybe he's nicer.
I don't know, and he's but so the paper is a German paper, so I mean you can find the theorem on inequality on Wikipedia or in some other books, right? The cool thing is that basically you can compute. I mean, the original theory is about just determinants, but I reformulated it in terms of the negative log determinant because that's sort of more intuitive for us now. Remember, we had this -1/2 log determinant of a matrix, right? And so what this shows us is that if we have some positive definite matrix, and it's symmetry as well, right? We can approximate the log determinant of the entire matrix by ignoring some off-diagonal blocks. So in this case, B is what we ignore, and then we have just the log determinant of A and C, so the diagonal terms. And this gives us a lower bound to the original log determinant. So this is, I think, maybe you already have an idea how we could use this, but this is kind of cool, right? I will get to that later. The second thing is a bit more involved, but it's not really, I think the intuition is more important here, right? This is just in the end to write down the theory entirely correctly. But what I want to sort of have you take away here is that this is a formalism on how to define block diagonal matrices. So basically, you take partitions of indices. So let's say we have P parameters, and every parameter has an index from 1 to P. And we make partitions. In this case, they also have to be contiguous, but also it's a minor detail. That means we just put, for example, the first layer into one subset, and the second layer into another subset, and so on. That allows us to form this partition P of S individual sets. And partition means they have to be disjoint sets, and their union has to make up the entire set again. Does that make sense? Like partition is something that's familiar to people? Okay.
What is partition?
Partition is basically you take a set, right, and you split it up into things, and that's already the partition basically. And by the definition, it's not allowed that there's one that sort of elements are shared between sets, so they have to be disjoint, and you cannot leave out any elements, so they have to in their union make up the original set. So it's really like I mean the word partition is I think very descriptive already. So that's why I meant this. This is really just get the intuition here right.
So H is the Hessian matrix.
It's in this case it's any matrix, and it will be different matrices later. But right now, let's say it's a Hessian. Yes.
Just do a block diagonal approximation.
Exactly. So you're writing just like this is just a way of constructing any type of block diagonal approximation, right? And so what's important here is that I can refine so-called refined partitions. So I can start with the full set. So the full set is by definition also a partition, and now I can maybe half it, and I have half it again, and I half it again, and so on. And in the end, I get a diagonal approximation. That means every partition set just is one index. So that's what I mean here, where PS is just S. That then gives you a diagonal approximation of your matrix. And so this is just something to sort of control the size of blocks and so on that will be useful later. So with these things, we can directly get something that is sort of interesting, which is very similar to variational inference. We can say that structured Laplace approximations are lower bounds, right? Because the reason is first, due to Fisher's inequality, we have this log determinant lower bound by ignoring off-diagonal terms. But as I mentioned, we can if we ignore the white parts, off-diagonal parts, we get a lower bound. And the more we ignore, the lower sort of the bound gets. So that's why the partitioning is important. You can refine every set and make it even smaller, ignore even more correlations. And then in the end, you end up with this diagonal. That's sort of the loosest bound, basically, in this particular case. What is the comment, MT?
So it's just on the log deck, right? So
it's just on the log deck.
It's not on the fit, the data fit term.
It's not on the data fit term. Exactly.
You're coming up with something, so I didn't want to.
No. It's just on the log determinant term. So it's basically for a Laplace approximation at a fixed point. That's why L, the L term, the data fit term is fixed here. You just lower bound the log determinant part, yeah.
And this requires H to be positive definite, I guess.
Exactly, yes, yeah. For the Fisher's inequality, you need that. I mean, but also for the Laplace approximation, you need that anyway. So there's no way around that. That's a shared assumption, I would say. And so if you, in practice, sort of try this out and see how this looks like, I have on the top here the prior precision. So that's sort of like one hyperparameter you would choose, and in the bottom I have rotational invariance for this invariance learning paper. And what you can see is the mode for the marginal likelihood, so what you would choose for the prior precision and rotational invariance is sort of different in both cases. And for the prior precision, they're all relatively similar here for full block diagonal or Kronecker factors, so K-fac. But then diagonal has a huge slack and sort of tends to choose precisions that are higher, so it leads to much more regularization and usually also to underfitting, which is something that we've also seen before, which is kind of interesting, sort of confirming that with these inequalities.
So this is the truth somehow, right? It's not implying from here.
Which one?
This is just an experiment that you run.
This is an experiment, exactly, yeah. Yeah, but we cannot quantify it. I mean, we can quantify theoretically also the slack, but in this case, like, this is an example where you can compute all the quantities exactly. And but for rotational invariance, you still have a huge slack, right? You go from -2 roughly to -12, but the mode is the same. So sometimes diagonal approximations can actually work equally well. So it really depends, again, on the problem that you are dealing with. Yeah, I think maybe what's interesting to take away is, I mean, it's just like similar to like variational inference, right? It's not that surprising that this is the case, right? But it is interesting because you could see a lot of these effects in experiments as well. Before that. Okay, so now I promised some duality, but we're almost there, but a bit more, right? So this is just sort of warm up now. So this is the like not very surprising stuff. Now I have to I want to reformulate this Laplace marginal light approximation. So we had this loss term, we have the expensive log determinant and some constant that we don't care about. And so the way we can actually write this as well is, because we use the Gauss-Newton approximation or Fisher approximation, doesn't really matter, or empirical Fisher. It's a log determinant of some kind of outer product plus P naught, which is Hessian of the log prior, right? So I'm going to define these symbols as well for you. So J here are the stacked Jacobians. That means for every data point, you compute the Jacobian of the neural network, so of fx and theta. Lambda are the loss Hessians, right? So they are, it's a huge matrix, data points times outputs times data points times outputs. So it's very big, but you would never actually compute this. So it's really just for the theoretical aspect. And then the prior is usually something diagonal, right? So this will be also, in principle, very big, but you never really have to write it out or materialize this matrix. So is this, like, are people familiar with this notation, or does this make sense? So Jacobians J, lambda, like second derivative of the loss, and P naught is just like prior Hessian, or log prior Hessian. Yeah, is that fine? So is there anything that you see if you look at the log determinants here? Empty, you're not allowed to answer. Unless you don't know the answer, then I would like to know that. Any ideas? Yeah, perfect. Like Woodbury or matrix determinant lemma or whatever you want to do. That's, I think, one of the things that MT would call duality, right? So we just take this log determinant term and we can rewrite it as something which is looking relatively similar to neural tangent kernel, right? So what we have, instead of an outer product of Jacobians, now we have an inner product, so it's not J chances of J, which is then scaled by the inverse of the prior. This doesn't really matter, like this is also the same case in for example, in kernel-ridge regression. And then this lambda term you could also ignore, because for like the neural tangent kernel theory, right, people have regression and then lambda is simple and falls away. And so I call this NTK because it's just very similar to this.
Finite.
Finite empirical NTK, yeah, exactly. But so the main thing here is that we can kind of now choose between computing the log determinant of a P by P matrix or an NC by NC matrix, right? So you can imagine there are certainly applications if you have very small data set sizes and few outputs C, then you would probably choose the NTK variant. And if you have very few parameters, you would choose the GGN or the Hessian variant. Right? So this is really the typical consideration you also have in kernel ridge regression or Gaussian process regression. But still, if we now think of deep learning, right, we have N millions or more, right? A lot of data points. We have C, which are outputs, also a lot of classes or tokens we want to predict, so 50,000 or thousands of them. And P is also millions, right? So we can't, like this is nice, right? But we can't really do much with it in the deep learning scenario. It's just sort of convenient that we can switch between two views depending on the problem. We can sort of see which one is more complex and more expensive to compute, and one will be always cheaper than the other. And maybe for small data problems, this is interesting. But so what we basically now can do is, because we have this right-hand side, we can again, it's in this case a bit more involved, but we can again use the same theory as before. So we can partition the kernel into different blocks, right? And get lower bounds on this that we can then optimize. And this is basically what we're doing here. We do partitioning now, it's called B as opposed to P before, that partitions data points and outputs. So the first case is basically getting a lower bound by only having correlation between data points and not across data points and outputs. So this is what, for example, if you read the Gaussian process book, there is multi-class classification in there. They would not compute the full kernel because it's way too expensive. They would compute the kernel per class. And this is basically the bound that you would get in this case. And you can make this sort of even, you can partition, you make the partition even finer. That means you take maybe a subset of these n data points and you go further to the right until you have a diagonal, which probably makes no sense in this case because it's just sort of the individual variances of data points. But sort of the same principle, the same methodology applies here, and we can lower bound by doing smaller and smaller partitions. And if you now again do the same experiment, you can see that actually taking 1% of the data points in this setting is still better than doing a diagonal approximation, right? So better do something in function space with a huge, like usually smaller subset of the data, as opposed to no modeling of sort of correlations, at least in this setting, right? And again, in the variance learning, it seems very simple. It doesn't really make a difference. As long as you have more than roughly 10 data points, you can figure out the rotational invariance that you need. If you have only one data point, you cannot. So it also breaks at some point.
Is that subset of this case random, or is it also selecting?
This is a great question. You can of course, and this is a very interesting relationship to Gaussian processes as well. You can choose, in theory, it's basically allowed to choose the partition to maximize the bound, right? So you can, for example, think of like class-wise sets or finding out which ones are most correlated. You can do that, and I tried that a bit as well. In this case, it's just random. So just random partitions, and this is also, but just because it's the most convenient, you don't do anything, right? So you can just do mini batch gradient descent in this case. I think that's also like the thing that's that was so exciting to me about this. If you write out this log determinant, so for some, let's say for this one here, the class-wise, you can write this as a sum of log determinants, right? And what that just means is you can sample subsets, so basically the partitions that you've defined, and compute the log determinant over them individually and get an expectation the same thing. So that means you can do mini batch SGD on hyperparameters. Right? I think that's sort of like the main thing that you can do with this, and the most exciting thing to me is that I don't need to take all my data to get the Laplace approximation. I can take some random subset and I get a lower bound that's of course not as good as the full data set, but I can sort of get an unbiased stochastic estimate of that. And yeah, so that makes things much faster, right? So you can imagine if I take like a subset of M So in this case, 10%, this is significantly faster than doing the full data set. And so I just want to, I just want to quickly jump over something that you can do, because it's too involved, but it's also kind of funny that you can do this. This is basically what we've just shown, right? So we have here this duality. So this is equal to this, right? And then on the left we go in the parametric space. We do this parametric bounding. On the right we do this kernel space. We do the kernel bounding, right? And so both views I think are useful for different scenarios, right? Depending on your number of data points, number of parameters, and so on. And now you can also do something more. You can basically use duality twice. So you go to the other space, you form a lower bound, and you choose any point here, whatever your fine-grained partition will be, and move that back via duality to the parametric space. So what we can do is we can do stochastic parametric Laplace approximations. And it turns out they're not that loose, actually. So what we have here is a block diagonal, so basically layer-wise, you can only model the correlations. And they look almost the same as for the full NTK that I've shown before. And so we can also do this with k-fact, right? So that means you can, with sort of this theory, you can use k-fact on subsets of data and optimize the hyperparameters with that. So it makes things much faster, right? And to sort of show how greatly you can increase the choice of estimators, this is sort of a Pareto plot. So you have on the x-axis the runtime of the estimator to compute one marginal likelihood gradient. On the y-axis you have the estimate of the negative of marginal likelihood. So you can see how much slack you have then when you compute this. And in color I show the batch size. So before we only use the black ones. So this one, I believe, as well. I think some diagonal up there, and then this k-fact one. And you can see that the new estimators that are based on subsets of data are somewhat like you can find new Pareto optimal estimators, and you have a much larger design space than before, right? Before I had to always do the full batch estimator. And now I can choose something that's a bit worse, but maybe 10 times faster. That's usually worth it. Yes, so another thing that sort of seems to, it seems to work at least in this invariance learning setting quite well, is very similar to the deep learning lesson, that it pays off to do more SGD steps than doing few exact gradient steps. So better form this lower bound, do stochastic gradient steps, as opposed to computing over your full data set size, the marginal likelihood approximation, and compute one gradient with that. So you can get much better performance. As you can see, NTK 401 is, M is equal to 400, so it's 400 data points, and for k-fact the same, so we don't take the full data set size. And even when we increase the subset size of C410 here, doing more steps, as in this case here, and I think in all cases, pays off more, although you have this additional lower bound. It also allowed to sort of apply marginal likelihood estimation to larger data sets or larger models than before, even for invariance learning. So invariance learning is relatively expensive as a procedure, and we can get like 20x or even more speedups compared to before. And in case of like learning the prior for time being image, that you can get a bit better than not tuning the prior basically. And I think the interesting part is really here in this invariance learning setting, because that's where people have built ad hoc methods like Ogorino, which just sort of penalizes your augmentation distribution, and in this data set actually didn't work anymore, so it's worse than the baseline, or partition neural network inference, which is also a marginal likelihood estimate, but yeah, you can sort of perform better by using these lower bounds, which are relatively cheap, in this case by quite a margin. Okay, yes?
How much of this do you think is actually due to like some basic principles, and how much of this is due to the fact that you're essentially looking at data sets that are extremely balanced, highly redundant, massively?
Sorry, TLDR, is there, like, do you think there's a basic principle, or do you think you're just looking at, like, sort of get lucky by the fact that you're looking at data sets that are super balanced, like highly oversampled, like lots of redundancy and so on? Like you can, like.
Did you say basic or Bayesian? Sorry, what did you say? Basic. I mean, to be honest, I would only know if I evaluated on all data sets, right? I think, like, from the deep learning aspect, I would say it could, of course, be like relatively random in this case. There are some, you can sort of do the algebra, especially for the invariance learning part, and you can sort of see what makes the model learn the invariances, and I think it makes a lot of sense. So I think in that case, it's really the principle. It's about, basically, you can look at the Jacobians and see why it will be optimized like this. For the prior, I couldn't really tell you why it can help so much to optimize regularization.
Specifically on the last slide, for instance, like to go back one slide, right? I mean, it seems like that takeaway, like more SGD steps, like fewer exact gradient steps, and so on. Like that seems to me intuitively to be very heavily tied by the fact that like there's so much redundancy and there's so much balance that like I can get away with really shitty, randomly sampled small subsets and still have a fairly good gradient because of this, right? Like, but if my data is not so well balanced and like not so redundant, then any sort of like small take is going to be super biased towards something really bad.
Okay, sorry. So if it's about this, then I completely agree. I think this is the case because in this case, the task is to learn the redundancy in the data, right? So what we're doing is we're learning invariances, right? And there are only invariances if your data is redundant. If it's not redundant, there's no invariance to learn, and then it will not work. Like, I mean, then it will not learn anything, essentially. So redundancy is basically, right, you have, as I mentioned, like this cat and dog example, you have a lot of rotated versions of dogs or similar dogs, right? This is redundancy, and this is what you exploit and will learn by SGD in this case. If you didn't have that, let's say you have always an entirely different dog breed, then the invariance distribution is very complex and maybe you cannot learn it. And then you also probably will fail with the SGD and even with the full wedge estimator. So I think, yeah, I'm not sure how I would answer the original question, but there has to be a redundancy for that example in general. All right, so yeah, I'm almost at the end now. Just a few things I wanted to mention, maybe interesting for discussion as well. I think generally it's worth thinking about what and where we can do with Bayesian model selection in general. What are applications that are sort of meaningful to tackle with this that are not possible without it? I think one of the examples I've shown was this biological factorization model. That is one thing where you could really not get the same thing without it. I think that is kind of cool. Also, it would be cool to have some kind of unified algorithm that allows you to optimize parameters and hide parameters at the same time, so that you don't really need to specify that. For example, for weight decay, right? Weight decay is something that's very hard to set, but it would be cool if we can just sort of put it into the algorithm as well and not over or underfit. And also, I think it would be nice if other approximate inference methods would work for model selection. So variational inference, I've tried a lot and never really works. The elbow is not giving you the right criterion. It seems like you can't really optimize it. And the question might be there, is it the diagonal, right? I mean, you've seen the slack of the diagonal is just huge. So if you want to optimize the prior with an elbow with a diagonal posterior approximation, maybe that's the problem, right? Maybe you need something like KFAC. And then also something that's completely different from deep learning, like maybe these lower bounds are interesting also to scale generalized linear models in particular. If you have a lot of features and a lot of data points, so N and P are both huge, maybe you can still do something Bayesian by using these lower bounds. And I think if somebody's interested in that, maybe that's also a possible application of that. I haven't really explored that much. All right, and then, yeah, I mean, I really have to also thank all of my collaborators that are in these references. So on the top, I have these methods. So these are like the margin likelihood estimators. With Vincent, I've worked a lot with MT as well. And then on invariance learning, Tycho is definitely important to mention. And yeah, if you're interested in the second blue one is this duality idea of using for the faster margin likelihood estimates. Okay.
Any other questions that maybe we have time for one or two?
Yeah.
Yeah, thank you for the talk. I was wondering some of the things you were mentioning about, training, doing model selection, while training, things like that. And one of the main, so I come from a GP background, so like in Gaussian processes, usually we'll consider VI as the only method that can like learn the posterior and optimize the hyperparameter at the same time. I feel like at some point, in terms of approximation.
Yeah, no.
Yeah, and then at some point, people would tout this as a very good property to have, and I think nowadays people are starting to get into the opposite camp. Maybe we shouldn't optimize the prior at the same time. So I just wanted to ask, like, what's your outlook on this in PNN, especially in the fast approximation?
Yeah, it's a good question. Why do people say for GPs they shouldn't be doing this? I mean, what's exactly the rationale behind it?
You just overfit sometimes.
I see. Well, I mean, overfitting can certainly happen, right? I mean, this is not magic, right? In the end, as we all agree, right? This is sort of a method that does work and doesn't work in different cases. I think the main problem that I've seen in my experience in terms of like when it doesn't work is really when some of the assumptions are not met. Like, for example, if you do a standard data augmentation, right? You average losses. Then this is one case where with the normal marginalization, it becomes a bit tricky to optimize that because you don't really know what's your data set size, right? So the scaling factors can be off. Another setting was actually layer norm and batch norm layers because they just don't make much sense with the prior, right? But these are all things I believe mostly it's just about figuring out what's wrong in the probabilistic model and sort of trying to fix that and maybe not have a weight space prior if you have a layer norm parameter and stuff like this. So I guess also in GPs it's the same thing, right? Depending on the model and the problem, it might or might not work. And I think it will be interesting to figure out where this can help and where this maybe cannot help. And I think there are certainly cases that I tried and it didn't work. But there's also cases where it worked very well and enabled something new, right? I think as with every method. Yeah. Yes.
Thank you for your talk. So do you find this marginalizing calculation based on Laplace being not able to capture the multiplicity distribution to be serious? So we have to deal with that sometime.
Yeah, I mean, it's definitely a serious limitation in principle, right? So that's of course a fact. I have one interesting piece of empirical evidence there that I found was quite interesting. So if you train a bunch of models, so when we estimate basically the error bars in our experiment, you train a bunch of models with this marginal likelihood, and you evaluate them on the test set, right? On the test set, you have some sort of variance actually. So different trained models will have different performance on the test set by, I don't know, between, for example, CIFA between can be 92 to 95, anything like that, right? But the marginal likelihood variance was much lower actually. It was very similar for all the models in the end, which is kind of interesting. So it didn't seem to matter much which mode you pick in the end. The marginal likelihood seems to be, or the approximation seems to be relatively similar, which was surprising. So I think for this particular, it doesn't have to be an issue. And I mean, you can also always ensemble it, right? If you want to ensemble it, just initialize multiple models and train them in parallel, not jointly. That would be probably hard.
Well, I'm not sure about the calculation, but if you have like multiple lower bounds, like ensemble Laplace from ensemble Laplace approximations,
yeah,
be able to construct another lower bound using those
mixture of Gaussian. Well, I wouldn't know right away. I would have to think about it. I guess, yeah, I don't know if it would. It depends on how you set up your ensemble, right? So if you set up your ensemble in a way that you average log it, so you average the function, as opposed to having them separate in terms of their losses or likelihoods, then I think it would work. You could do the same thing. That's essentially what happens here, right? It's quite a bit back, but basically, in ensemble, you could see that as this expectation over functions, and then now, I mean, the notation doesn't fit, but basically you have sum over or like an average over individual models, and then this thing should still work in principle. Yeah. Here it's over x prime, so it's data augmentation distribution. But you can imagine you can put a discrete distribution over different thetas, so it's like discretely choose between 5 different parameter sets. So yeah, I think it should still work.
Cool. Let's thank Alex again.
So, okay, so we're done with first. They're right on time, right? Let's give ourselves a hand.